Good evening, everyone, and welcome all of you to the section 3C track on hardware for AI/ML. Myself, Pawan Kumar. I work as a senior director at Qualcomm, leading the GPU systems and R&D team, and I'll be the session chair for this track. And with me is Zia. He'll introduce himself. Both of us will be the session chairs for this session. Thank you.
Yeah. Good evening. I'm Dr. Zia Abbas from IIIT Hyderabad. Okay, so let's start. Invited speaker is Professor Alex James. It's my honor to introduce him. Professor Alex James is a professor of AI hardware at the School of Electronic Systems and Automation and Dean Academics at Digital University, Kerala. He received the PhD degree from Queensland Micro and Nanotechnology Centre, Griffith University, Brisbane, Australia. He works in the broad area of brain-inspired systems, memory-assisted systems, intelligent devices, analog circuits, and imaging systems. He had Maker Village that support over 80+ hardware startup. He's a chief investigator of MITI-funded National Center for Excellence in Intelligent IoT Sensors and India Innovation Center for Graphene, developing new products to the market. Dr. James was founding chair of IEEE Kerala Section Circuit and System Society chapter. He's a member of IEEE CAS Technical Committee on Nonlinear Circuit and Systems, IEEE CAS Technical Committee on Cellular, Nanoscale Networks, and Memristor Array Computing, and IEEE Consumer Technology Society Technical Committee on Quantum in Consumer Technology, and Technical Committee on Machine Learning, Deep Learning, and AI in CE. He was an editor member of Information Fusion, Elsevier, and is an associate editor for Frontier in Nanoscience. IEEE Access, IEEE Transitions on Emerging Topics in Computation Intelligence, IEEE Transitions on Circuit and System 1. He was awarded the Best Associate Editor in IEEE TCAS 1 for 2021. He has been active as a reviewer and TCP for IEEE ICCE, IEEE ISCAS, IEEE ICECS, IEEE APC CAS, etc. He is a senior member of IEEE, life member of ACM, senior fellow of HEA, fellow of British Computer Society, and fellow of IET. He will be the lead TPC chair along with the Professor Shanti Pavan and Massimo Aliotto for the IEEE APC CAS 2023 to be held in Hyderabad in the month of November 2023. You are cordially invited. Please, it's over to you.
The talk is not going to be very technical, but there will be some technical elements here and there. So please bear with me, if some things are not clear. So I'll be fairly quick to introduce the thing, and if there are questions, we can take it as we go along. So what I'll discuss today is next generation AI hardware. So you'll wonder, what is next generation, right? So if you, this is a very famous work, probably in 2018 by Velu, a very nice article, you should read this. So it kind of summarizes why we need to think about in-memory or neuromorphic and so on and so forth. Mainly you'll see three things. One is the limits of the Moore's law coming into picture, the memory wall, the heat wall, and all these current technologies that we have, whether we are using GPU, CPU, whether it's CMOS technology, all of them, put in a neural, if you want to implement a neural network, you will see that you will face all these problems coming in there, and a lot of optimization time goes into fixing those things. You playing with architectures, playing with various kind of algorithms, trying to fit into solving those. Now, what the promise that the alternative computing approaches offer is that since we are talking about more and more sensors coming into picture, you are thinking about like a large amount of data being processed. You want like you want to make your devices more and more intelligent, so some kind of processing needs to go into your edge devices. So when you have all these things, you would want to do efficient computing at all levels, and that's where things like, okay, can we make it energy efficient? Can we make it like area efficient? Becomes more and more important with increasing data. So when you look at like the AI literature itself, you would see most of them use AI today as a tool. Why AI has grown in the last several over a decade is like it's easy to use, and you can find like a lot of applications that is driven by data, where you don't have to be very frank, like as far as tool is there, you try out the tool. Try 10 tools, 10 algorithms, one of them will work in one way or the other, you go ahead. Now, building an AI, that's really an AI, that's a different ball game altogether, and you would see out of hundreds of thousands of papers that are coming out, very few only like address those fundamental questions. Really trying to solve like the problems in with like AI. And obviously like the learning curve and all those things that's required for that is also very high. Now, coming to the quick definition of the intelligence over the years, like which is where like the AI is built upon, you would see Hunter's definition, which kind of like looks very simple but very difficult to implement. So if you look at like intelligence measures an agent's ability to achieve goals in a range of environment, wide range of environment. Now just take a moment and think about all the AI systems that you're familiar with. Think about this part, like range of environments. How many of the AI systems actually work in all the different range of environment? You would see like a lot of them works very well in a very specific set of conditions, constraints, and they are not generalizable. Whether you build a hardware, whether you build a software around these, like the problem remains the same. So the generalization is a big challenge, and you would see the idea is not something new. It goes back into the Greek philosophy of tabula rasa, where you have a blank slate. You can just go and write anything, just erase it and again write anything, right? And then you also have the other idea of evolution-driven intelligence. Like one classic example is you build like a lot of small intelligent systems, put them together, you solve more complex problems. So over a period of time, you have a lot of small specialized systems together. You combine in different ways, whether it's in a hierarchical, whether it's in a parallel, combination of those different kind of architectures, and maybe you'll be able to solve very complex problems. Now the problem is we don't have the means to solve this yet, right? Because the complexity, what we understand, if you try to put together mathematically the entire like brain, we still don't know how to put all those things together. The science of complexity is still not settled to understand the brain. The whole thing of consciousness that people talk about, we still don't know the complete science around it. So if you are going to build like a AI, which is going to be sensible like humans, we are far from it, right? So the AI what we are talking about is something very different from how the human brain is working. So that's fundamental understanding that we need to agree upon. So if you say brain, AI is like brain, that is not right at this point. We are far from it. So the link between realism and abstraction, you can see here like a picture. Most of you will be able to recognize that, okay, it looks similar. There is that face embedded into that picture. Whereas like in reality, it's a very much abstract. You look at the other side of the picture and you'll say, okay, that's still like a picture of a person, somewhat encoded, right? Now put that to a computer algorithm, depending on your algorithm, this will give you very different results. It's not going to say with conviction that like, okay, this could be this or this could be that. And you could train it for many algorithms. You can come up with rules and train it for that particular image, but then change the image, you have a different story altogether. So one of the major challenges, like, how do we move our AI to AGI or general intelligence? So possibly neuromorphic computing could be one approach. Where obviously from a hardware point of view, the bottleneck from data transmission and all those things, there is some advantage. But what people don't tell you is that, like, if you want to reduce that, you're compensating on something else, which could be most likely the control circuits and other peripheral circuits that you need to build around it to work. And that usually tend to be much, much larger than the actual compute itself. So some of the things that you would see here, like, when we are thinking about like any kind of like brain-like systems, you would see certain interesting properties. So for a start, like, this is all kind of feedbacks going in. There is a feed-forward mechanism, there is a feedback mechanism. So if you don't incorporate both of this, you're not going to mimic like the neural networks of the brain. So underlying, there is definitely a recurrent nature to it. There is always a feedback. Now, another interesting thing about the brain is it keeps on changing. So if you look at your brain, every 20 minutes, it gets rewired. So by the time this talk is finished, you go to the next talk, your brain is different. Right? So it keeps on changing, but our neural networks don't. All the artificial neural networks that we have. So fundamentally, the dynamic nature is missing in a lot of neural networks when we implement it. So that's one thing that we have to realize. You can have so many different functions possible with the same biological networks that we have. So it's functionally infinite. And it's dynamic, it's complex, and it's recurrent. And neuroscience is still not settled on all these kind of things. Whether the brain is functionally, is it modular, is it hierarchical? You would find like debates and debates on both sides. Saying like, some of them saying like, it's a hierarchy, some of them saying it's modularized, some of them saying it's not, all sort of things. Then another is sparsity. Sparsity is a very difficult problem to solve when it comes to implementation. The simple thing is this, like, if you want to look at digital implementation, you have a lot of ones and zeros, and you're doing a computation multiplying zeros with many things. Now, that 0 multiplied by anything is 0. Now, the question is, do you want to compute? Right? So how do you build like architectures which can be efficient to do the sparsity? Then spiking neurons, is it the way to go about? Like the brain has spikes. So a lot of arguments for having spikes is that it is more energy efficient and so on and so forth. But always it comes to the but, like how do you program it? How do you make it training efficient? Do we have like training algorithms which can be scaled? So right now, if you look at the almost all work in spiking neural network, the artificial SNNs and all those things that people have done, the training part is always a trick. You kind of like, find a way to encode. Still, we haven't solved it, right? We haven't solved like how that training can be done in real time, how you can update in real time, like how a brain does. Because imagine like your network keeps on changing, right? Every 20 minutes, the network changes. How do you retrain it? So your training has to have elements to it, have certain kind of like update schemes or methodology which is energy efficient. At the same time, like, you don't want to take it to a cloud to train it. right? If you want to build a brain, it has to happen in the brain, like in the same hardware. So the problem look very different when you see it in that way. So if you want to put together like what we are doing overall in this field, so a large number of work is basically energy efficient implementation of algorithms. All the AI algorithms like what we have today, we're trying to make it efficient implementation, whether there is a deep learning accelerators or ML accelerators. And there are two approaches. You make it general purpose or ASIC, right? ASIC obviously going to be like much more efficient for specific applications. But if you are going to sell it as a product company, probably you want to make it general purpose so that it can be applied to various kind of problems. And you would see like applications are the drivers, so you cannot like remove applications out of picture. So application becomes like very important part. Speed, energy, size becomes kind of like a very important part when it comes to these accelerators. And today you would see dominated by digital or system on chip like implementations more because you know that this works. The reliability is more. You can actually like sell it as like a real thing. Now the other side, like going ahead, thinking ahead, like where we are going. So you would see whole sort of like different things going towards like super intelligence and things which you need to think about now. So will quantum be able to help in terms of accelerating the learning? Can we stack like weak AI systems to create like strong AI? Can we have human intelligence? Can we have human machine intelligence? Use the brain. There is a nice some works happening where people are trying to connect the brain and like chips and combine it together to create like a human computing systems. So use the power of biology as well as machines to create like a super intelligence. Can that be general purpose ASIC? And the question about like size and speed may not exist in this case. Like just think about it. Our brain is very slow, but it does much more powerful things than a processor which would be running at like gigahertz. So the brain has most of the parts as in analog nature. So if you want to mimic a lot of brain, you would need analog elements, not necessarily as a silicon itself. You may be looking at different materials. You may be looking at like biology to come in, all sort of things. So going ahead, like that would be the kind of and energy is an important thing for that. So if you build the complexity more and more, it may be bulky in size, but it has to be extremely energy efficient. If you want to pack more, if you want to process more, this becomes a very critical thing. So memory-based computing can be an approach. So one of the things like what we do is like we explore this with crossbars, right? Different kind of crossbars. But these devices often have like device-to-device variability. You would see a large number of devices that can be fit into it. All the resistance changing devices can be fit into this philosophy. There is an ideal, this is one thing that one has to understand when we talk about memristors. There are properties of the memristors that you can use. You don't have to use the whole properties. Like you don't want to chase the real ideal like device. You can use those properties in understanding and building like better computing systems. And here the thing is like you can do the computing near to the sensor. That is could be one application where you can put a lot of analog kind of systems going in. So interestingly, in this work, what we showed was like all the variabilities that were there before. You can compensate it largely by using a very simple technique, just connecting the rows of the crossbar. Okay, the maths is like bit, when you just do this, the maths becomes a bit complicated, and it shows some interesting stuff like interesting geometrical, mathematical transforms coming into picture where. Just taking 8 stable levels of or 4 stable levels of a memory, resistive change memory, you could create 70,000 stable states by combining levels. Which means you can, in fact, build any analog neural networks with such crossbars. So that was an example there. You can see like a convolution neural network that is built with such arrays, which gives you exact same accuracy, performance accuracy as that of a algorithm, even under a lot of variabilities that you would face in the devices. In fact, you can then build many other different types of networks. LSTM, you can build HTMs, you can build GANs, all in analog. You're looking at maybe 3 million, 4 million devices, everything the crossbars working in analog. The catch is you have one thing that is hidden is you have to program these, and programming requires a lot of digital on the other side, right? So that is always there. And another thing is you can automate. When you create a lot of analog, the problem is variabilities. You need to take hardware variabilities as well as hardware performance indicators, as well as you need to take into account the software performance, the accuracy, precision, all those things. You need to. It's a multi-objective optimization, right? So one way to do that is you can build the cells, basic cells, give various options of the standard cells, and use those standard cells to find what is the best architectures, what is the best combinations for your neural network that you are trying to build, and automate the whole thing. So we build a tool chain where you could just do that. You can actually give the set of standard cells, and from there, it will give a recommendation of what is the energy efficient, for example, if that's what you're chasing. If you're chasing, say, aging as a factor, you can select it. So you can combine it and get optimum. So right now where we are in this field is AI 1.0, which you can say neuromorphic 1, neuromorphic 2. So if someone is saying AI is matured, it's not. We are very, very early in the process. There is so much more to cover. If you are thinking about beating brain, we have to go various levels, and it may not be just silicon that we are looking at. We have to look at various other technologies as well more carefully into it. Going from the material stack to device stack, all the way up to architectures, there has to be plenty of innovations happening if we were to reach there. So these are some of the papers in the last few years, in this area you can that we have done. You can have a look. It's my group recently taken a photo. Many of these guys are working hard to do some of this work. Thank you.
You mentioned that continuous training is something still needs to be worked on. I thought it was something there. I mean, AI engines today are continuously learning, right? Training is happening all the time. So.
Okay, so I'll just rephrase that into the issue, right? There are algorithms, right? There are learning algorithms in real time. Imagine the current neural networks, we are looking at say 20 layers or 50 layers or 70 layers, right? Layers is not the challenge. It's actually the number of neurons that we are chasing is a problem. So if we were to create a chip, which is equivalent to brain, right? We are looking at billions of neurons. Do we, for a start, have a chip? No, right? So if we were to train a billions of neurons, do we have an algorithm which can do that? Currently, we don't. Right? So, and if you were to put that into a chip, it's not going to be efficient with backpropagation and all those things. So, and this is a core thing, right? So if you look at backpropagation, it's trying to find a optimum, global optimum. But our brain is working just opposite, it's working against the global optimum. So every time a noise comes in, it's happy to jump around, try it, but algorithms don't. So clearly, like, while like it is working, like to optimize into like something very specific, in real world, this is not how we work.
Right.
So, and that is not really solved.
Right, understood.
Yeah, I have one question at the back.
Yeah.
Thank you. Exist in neuromorphic?
Yeah, so when we talk about neuromorphic today, like, if you look at the history of neuromorphic, when people talk about it used to be only spikes. Today it's not that. Many of the networks that, neural networks that are created like CNNs and LSTMs and all those things, their foundations has been inspired by how brain works. So there has been a lot of work which you would see in neuroscience and others, like, what people have done is they try to compare like the functionalities of, like, say, cortical networks and map it to CNN and say that, okay, this layers of CNN is equivalent to this functional layers in the brain. So you can always draw that mapping and say that, okay, it's similar.
So there is no hard line about
There
spikes.
is no hard line. I mean, it would be a very stupid thing to do that.
Yeah.
So we'll kill the innovations if you do that.
And one more, like, you spoke about spike-based computation, mostly really limited to hardware. So can you throw some light about compiler stages, or do you have any compiler framework to decode this spikes to OS or like some kind of thing? Because we are talking about more processor and HPC frameworks later in future.
Right. So this is, I think you touched upon a very important part, especially the frameworks that we are looking at in terms of like software that goes on is to build that complexity. So if you could do everything in hardware, perfect world, right? But then can we build like a brain like 3D chip? Since we can't, so we have to rely on the software part because everything is planar anyway, right? So the chip is like, even if you stack few layers, it's still, largely planar compared to brain. So putting those things together, you definitely need like a framework which the software would provide. So the question of like, do we need the software? Like,
do we have any like?
Do we have? We have bits and pieces. It still needs to be largely developed, especially from a complexity point of view. For a single chip, or 2 or 3 chips, we have frameworks to do it. But if you are talking about like, a billion neurons, no. That's still far away from.
Thank you.
So, yeah, how in an array changes when we interface with the CMOS-based circuits?
Well, you need to look at the device carefully, like when you are like, trying to integrate into like CMOS. There are some of the devices are easily you can easily integrate. The programming pulses that you give, they usually are like higher voltage level.
Exactly.
Right? So if you are using a particular technology to program, obviously you need to have that voltage to program. Right? But then the read voltages are very low.
Yes, sir.
So which means like, most of those in inference, this is not an issue. Most of the CMOS is fine with that. Okay. So there are certain devices which you cannot, like 9 volt and 15 volt, like, there are devices that you would see. There are also devices where you can program in 1 volt or less.
Sir, one more thing is, I'm using 45 nanometer technology and I'm using 1T1R cell, basically resistive RAM, which require around 1.5 volt for programming. But the basic 45 nanometer technology supports around 1 volt. What kind of interfacing circuits people use?
No, that will just slow down your programming, right? You see, the idea of programming these devices is that, like, there is a trade-off between the voltage and the width of the pulse. So
yes.
You just like, increase the width of the pulse and you give more. So it means like it takes a lot more time to program your devices.
It's like number of pulses that we need to apply is more. That is the case. Sir, if we have a fabricated chip, the technique used for programming may apply, but if we are using simulation-based thing, how do we achieve that?
So I wouldn't suggest you to completely rely on like the simulations for especially like RE-RAMs. You need to look at like the data, at least like, some of the real devices and see like, what is the voltage range, what is like, programming cycles and all those things. In real, what happens is like many of these devices which claim to be like, multi-levels and things like this, they have a lot of variability. Right?
Yes, both.
So the variability will be there. So which means like, even if you come up with like a very idealistic simulation on the programming, this is not going to work in real. So you need to make your design variability aware. So it should be a variability aware like programming that you do. When you are programming the pulses and things like this, you need to build that conditional like, logic around it to program it.
So one last question.
If you don't mind, present a token of appreciation. Our next talk is on extending action recognition in the compressed domain. The speaker is Samuel Abrams. Samuel graduated from Penn State University with a bachelor's in computer engineering and a master's in computer science engineering. And his focus is on machine learning for action recognition. And currently is working as software engineer at AWS in Washington, DC. Welcome.
Hi, everyone. My name is Sam. I'm from Penn State. And today we're talking about extending action recognition in the compressed domain. So just to go through, we'll give a little bit of a background about video compression in general, action recognition and some of the previous attempts to model what is happening in a video, and some of the benefits and applications of this approach, and some of our results. So video compression, why do we use it? Video is giant, and it's everywhere, especially with the increase in streaming, just video playbacks in general. It needs to be compressed, and it's still too large. So there's still more work that needs to be done in compression, but if video is uncompressed, the internet would be unusable in most cases. So how is it done? Store a limited number of frames in their full state. We call these iframes. They're basically RGB images with bits of compression done, but they'd be recognizable to us. And then we're going to have motion information, which are basically just pieces of the iframe that are shifted around and basically only have the motion information modeled, so that we were able to reduce a lot of that, the spatial element. So which approaches have worked in the past? MPEG-4 Part 2 and H.264 are some of the older approaches that are still being used today, and we have some of the future work like HEVC and VP9. So how do we represent motion? We basically can break a frame up into a set of macro blocks and only store the offset of where they moved from some reference frame. So a P frame will reference its previous reference frame, and a B frame will reference something in the past and in the future, so they can be even smaller. And we can take these macro blocks and shift them around, but there's still going to be some missing elements from the reconstructed frames. We need some sort of offset, a residual error in this case, to make sure that if anything new is introduced to the image, we're able to model it without having any kind of artifacts or anything like that. So motion vectors and residuals are the two main parts of a P and a B frame, just representing motion. So we can compare some of the benchmark video compression codecs. We have MPEG-4 Part 2, a little bit older, not used in the mainstream as much. And basically, it's going to have constant-sized macro blocks for motion compensation, as well as a fixed number of, or a fixed rate at which iframes are encoded. So basically, we know that iframes are pretty big. They're RGB. We don't really need to store all that information. And in most settings, you're going to have one iframe for every 12 frames, so followed by 11 motion, basically, frames. And some cases this may be necessary, but in a lot of cases, we're just going to be having the same image over and over and over again. And I think the MPEG group figured out that they could do better. So H.264 does not have this requirement. It's able to only use iframes when they are completely necessary, when the scene shifts in a large amount or there's a large amount of motion. So they can really increase the compression ratio 2 to 3 times. And that's why H.264 is still used today, because it's a lot more efficient. So video action recognition, it's just as it sounds. It's trying to model which kind of action is happening in a video. There's plenty of applications in security and data analytics, robotics, anything that takes in video needs to know what's happening, especially as we want to interact with computers on a more personal level. Some of the challenges, video is very redundant. The background stays the same. Like if there's a video of me right now, only a tiny amount is actually changing. So just taking a full stack of frames and running them through some sort of image recognition network, like a ResNet or something, it's going to be very difficult to find any kind of motion. So several approaches have been done to try to remediate this. CNNs are one of the benchmark architectures that are used for this type of problem. So we'll look at a few of the previous approaches and kind of how they succeeded and how they can be improved. So this topic was started in the uncompressed domain. One of the earlier approaches was a 2-stream network, which took in one stream RGB frames and another pre-computed optical flow. So the RGB frames fully represented spatial information, whereas optical flow was for the motion or the temporal information. And these were a consensus was taken, and a prediction was made. 3D CNNs are also useful. They performed well, but they're very large. And you don't need to pre-compute any kind of optical flow because it's learning spatial and temporal simultaneously. But basically, we run into some of the problems we talked about before. Video is redundant. It's, you don't need that background in every case. So the paper that I kind of was inspired by to work on this, CoVR, decided to work in the compressed domain, using only a subset of the RGB frames and kind of that built-in pseudo-optical flow. It's blocky optical flow, but it's motion vectors and residuals, and they can provide a similar approximation without any kind of pre-processing. So, an important part to mention, all compressed work so far has been done in MPEG-4 Part 2. So, again, it's an improvement, but it still has a lot of it still has a lot of RGB frames to work with. Some other useful techniques just for video action recognition in general, both compressed and decompressed. Temporal segment networks, just take a sampling of different frames from throughout the video to attempt to cut out some of that background noise just by subsampling. And a temporal shift module is a way of injecting motion information into a stream of just frames, RGB frames, just by, after convolution, say, sharing some of the feature channels from adjacent frames, shift back and forth in an offline approach, and inject some information about what's happening in the next frame into the current one. And you will potentially not even need a second stream. You could have that, the benefits of a 3D network of learning spatially and temporally simultaneously, and just do that in a 2D network. So given all this, can we try to implement action recognition in H.264? There's less information present. You only have basically one iframe and maybe 200 motion frames afterwards. So definitely less information to work with, but we'll see if we can apply some of the things we know. So the proposed solution that we wanted to use was to reconstruct a certain amount of iframes without decompressing the entire stream. Pseudo iframes, as I coined them, can be generated just by accumulating a certain number of p frames up to where you'd like to decompress something, or quote unquote decompress it. and basically just take these and treat them as iframes, just see if they provide that same amount of information without having to decompress the entire stream. This was done as a two-stream network, so it was also, residuals were also used to kind of get a little more insight into what's happening in the stream. And the goals are to perform similarly well to MPEG-4 Part 2 approaches and win in terms of efficiency. So you can see a representation of how we are reconstructing these frames without decompressing the stream. You have some sort of reference frame, so that'd be an iframe or a different frame that we had already reconstructed. Take the motion vectors and residuals from the P frames in between to where you'd like to decompress, and simply apply the shifting and residual, and add the residual, and you can get a decent representation of what a frame at that spot would be. We experimented with several different approaches and found that using only the green channel actually produced a solid representation and had fewer artifacts, just potentially due to quantization or other small optimizations that are made by the decoder that we're not doing here. Using the green channel only allowed us, which is represented as grayscale here, allowed us to increase efficiency even further and get a good representation of what an iframe would look like at that spot. And there are more there's definitely variables to adjust here. One of these would be the frame count, being the number of frames you want to extract from a certain video clip. The data sets we use are pretty uniform in size, probably about 5 to 10 seconds in terms of length. So we used, as a benchmark, we used 8 frames per video, but we also tried 4 and 12. And instead of, so our process here is to use potentially every motion frame, that P frames and I frames, P frames, but we also tried with using a different frequency of P frames. So potentially use every other, every fourth, or even every 8th P frame, and see if we could reconstruct these I frames with good enough accuracy to potentially justify that, that saving, that lack of computation that we'd have to do. So some of the results from our work. So you can see just with our benchmark approach, we were able to perform relatively adequately compared to some of the MPEG-4 approaches, MPEG-4 Part 2 approaches, and that's only with 2 streams, whereas many of these are 3D networks, 3 or more streams, or use pre-computed optical flow. We can avoid all of those tasks. As you can see, we're the only approach that is attempted work on H.264, and even given the low amount of information present, the 2 to 3 times greater compression ratio, we're still able to perform adequately well on both data sets that are widely used in this discipline. And I guess in the second table, what we can take away is that for HMDV51, 8 frame count actually performed the most efficiently, and for UCF 101, a 4 frame count actually did perform the best. And this might be counterintuitive. It might seem like the more information you have, the better your results should be. But what the takeaway can be is that there's definitely an adjustment that needs to be made for any particular data set or video length you're working with, because you want, the way the temporal shifting works is you want a nice uniform gap between the motion that's occurring so that when you shift, you're still able to glean motion information. If you have too many frames, everything is too similar and you're not getting a lot of motion information from a shift, which is why you can see with 12 frames, there might not be enough motion happening between them to gain the optimal amount of information. And frame count, speed up relative to CoVR, which was the original MPEG-4 approach. You can see 8 is the number of segments they use, or 8 is the number of segments they use in our approach. Has a good speed up comparatively, especially when you start using fewer and fewer frames in your model. And in our second method of reconstructing iframes using a variable frequency of from the motion information, so say every other, every fourth, or every 8th P frame, This is definitely reducing the amount of computation that needs to be done greatly, and we're still keeping relatively adequate accuracies here. So as a conclusion, action recognition in H.264 is definitely possible, and it gives us an opportunity to really expand the use case of video action recognition in the compressed domain or in general, because everything is compressed at some point. So to not have to decompress is definitely it gives us a lot more opportunities to work with this tool. Cool, thank you so much.
Take a couple of questions.
Since YouTube and other clips are trying to move to VP9, have you had a chance to explore on VP9?
Yes. So again, this is just the number of iframes was the thing we focused on for the most part, but there are plenty of other optimizations being made with these codecs. I believe with VP9, there is a lot of intra-coding being done within a single frame, whereas certain macro blocks are being based off of others within a certain frame. I know that's one optimization. I'm not entirely sure of the others, but that's something we've not looked at yet, but I think it could definitely be useful in implementing that in the future.
Because the algorithm as you have it now would not work, would not translate directly to VP9.
I would need to verify that for certain, but that would definitely be a goal in the future, is using some of these more modern, still state-of-the-art codecs. Thanks.
Anyone else?
Models, like apart from action recognition, do you see other tasks on video translating to this encoded form, like video summarization or some other tasks, which can be done on top of the encoded video stream itself?
Definitely. I feel like video action recognition is very, a good starting point. But I know there's plenty of like mixed medium type of problems too with text. There's definitely a lot of approaches here. And I think as long as we can model this, the temporal space and the spatial area in the same networks, we'll be able to apply this to a lot of different problem statements. But I don't have any in particular right now. Thank you.
Pranos J. Evadur. So Pranos is currently working with CDAC Bangalore. His research areas include hardware accelerator for neural network applications, signal processing, image processing, digital design, etc.
Good afternoon, everyone. I'm from CDAC Bangalore. I'm Pranos. So currently today I'm presenting a paper on design and analysis of POSIT query processing engine for neural network applications. These are the total agenda. So I'll be giving an overview, then problem statement and what is the solution for that. Also what is the proposed solution, what we are proposing it, and the methodology for that, results, conclusions, and the references. This is the total overview of the work. So as we know, neural network or deep learning applications mainly compute, it's always a matrix multiplication application, which includes multiplications and additions. Most of the research is basically focused on the multiplication and addition data types. So in this work, we actually propose a POSIT data type and its multiplication and accumulation, the framework, and also the hardware architecture. So in this, we'll be processing a query-based addition, which is actually a wide accumulator-based addition, which can be integrated actually with any type of data type. And here we'll be actually integrating with POSIT data type. Okay, along with that, we'll be doing the performance analysis with floating point and also with the fixed point data types. So as I have already told, the basic design in any accelerator is a design, if you're going for a basic module, it will be always a basic multiplier and an adder which is accumulating again and again. That's called our vector multiplication, dot product operation. It will be accumulating again and again on a particular product. It will be P1 plus P2 plus P3, which will actually basically rolls down to a simple multiplier and a simple adder, which is accumulating again and again. So we have done a balanced hardware resource and performance centric for DNN accelerator using POSIT. So the POSIT processing engine for DNA accelerators. So as a result, this POSIT is actually, we can say that if you're having an n bit with a number, it will be divided into n, es. So you will have, it's a replication for the floating point arithmetic. You must be knowing about the floating point arithmetic. So you can use it as a replication for the floating point arithmetic. It can be replaced with POSIT. So POSIT processing engine is of different types. It's having 8,0, 16,1, or 32,2. This all can be used for replacing the floating point number system. In this, accumulation is actually done using a quire, which is a wide accumulator, so that there won't be rounding of errors in each accumulations. So if you are going for a matrix multiplication operation, you will be doing iterative multiplication and additions. In that case, you can get accumulation, or rounding of errors can get accumulated. In this case, by using quire processing engine, we are actually avoiding that. This is the whole hardware for POSIT quire processing engine. The whole hardware is divided into multiple parts. So first is the extraction part, similar to the floating point. We'll be extracting out different parts of the number system. So we'll be extracting the sign bit, we'll be extracting out the regime bits, and also we'll be extracting out the Mandelson bits and also fraction bits. Then it will be fed to a Mandelson multiplication unit, which is actually a fixed point multiplication. Also similarly, we'll be extracting out the scaling factor, which is a run of zeros or run of ones according to positive and negative numbers. We'll be having run of zeros and run of ones. We'll be detecting the number of run of zeros, and correspondingly we'll be generating the scaling factor. That will be fed to a quire register. A quire is an accumulator which is actually a fixed point accumulator, which is a wide accumulator which reduces the rounding of errors. The output of quire is again a fixed point number which we'll actually take it back, or else we'll actually represent it back in POSIT number, and then the POSIT number is again POSIT number will be again rounded off using our RNA techniques, rounding to nearest even number technique, similar to the floating point numbers. This is a comparison. So we have used multiple comparison techniques. Here we have used the POSIT along with floating point numbers and also with the fixed point numbers. So you can see 32-bit floating point number will be floating point processing unit will be using 2226 LUTs. We have done it in a VCU 118 FPGA board, and also registers are 1062. The same using 16-bit POSIT with quire will be giving 1344 LUTs and 407 registers with a frequency of 175. So we can see that this can be actually a replacement for the 32-bit floating point number system. And especially when you see the accuracy wise, you can see 16,1 POSIT will be giving exactly the same accuracy as floating point, 32-bit or single precision floating point, which is actually used, which is mostly used in our neural network applications. Similarly, if you're going with 8-bit POSIT also, you can see it's having LUTs as 67 LUTs with quire. So the same thing we can see that the accuracy is slightly dropped. In the next slide, we can see the accuracy is slightly dropped down compared to 32-bit floating point, but still we can see because of with the hardware acceleration or the hardware resources are very less compared to the floating point. So in this we have done software analysis on different architectures like LeNet 5, 5-layer CNN model for CIFAR10 architectures, and also alphabet recognition, and also AlexNet CIFAR10 architecture. This we can see accuracy of 32-bit floating point, the inference accuracy for 32-bit floating point is 98.98, whereas 16-bit floating point is 96.42. The same thing with our POSIT 8,0, we will be getting 95.70 accuracy, which is a slight drop in accuracy of 3%. Similarly, POSIT 16,1 will be giving exactly the same accuracy of 98.98. So in this we can see the 32-bit precision rolls down to actually 16-bit precision, and we are getting the same accuracy. The memory imprint and also the computation efficiency or processing engines and everything, the hardware acceleration is exactly the same, whereas the hardware resources are very less. So POSIT can be a replacement for the floating point. So we can see if you are using indate, the accuracy we can see. Sorry. Indate accuracy will be actually rolling down to 70% accuracy. So the same application, if you are going for indate, it will be going to 70% accuracy, and also if it is in 16 and all, it will be going to 78% accuracy. So with the same indate or 8-bit precision, we are actually getting the similar accuracy to floating point. So that is the advantage of POSIT here. Now the advantage of using quire here. So if you in normal multiply accumulate units will be again and again increasing the rounding of errors. So here we can see the absolute error and n samples. So if you are accumulating 4,000 samples, the absolute error without quire, that means without the wide accumulator register, will be increasing drastically. Whereas with quire will be very slight, it will be in the range of 0 to 1 range. In case of POSIT 8,0, whereas in case of 16,1 also you can see, with quire, the absolute errors over an accumulation of 4,000 samples will be very less, whereas without quire the accuracy will be dropping down considerably because of the rounding of errors. This comparison we can see that when we are using for DNN applications, when there is any CNN application or any FCLS or any RNN application, we can actually see when you are going for a larger matrix multiplication or when the number of times of accumulation is increasing, usage of quire is much more important in case of smaller bit precisions. Even if it is 8-bit precision or any kind of precision, usage of quire or a wide bit accumulation is very important. So that is a study which we have done. And the study is done using a Python library, soft POSIT library. In that we have done analysis for 16,1, 32,2, 8,0, and along with the comparison with the golden in 32-bit floating point golden data type. With that, we have done the absolute error variations. So in this, we can see POSIT 8,0 can be used for applications where slight accuracy drop is okay. I mean, a slight accuracy drop is accommodatable. Whereas 16,1 or 32,2 and 64,3 will give 16,1 will give exactly the same results as single precision floating point. So 16,1 with 16-bit, we are getting exactly the same accuracy as 32-bit floating point, which actually reduces the memory imprint and everything. So 16,1 can be used in any applications for inferencing, where accuracy is the important thing. Whereas 8,0 can be used for applications where accuracy can be slightly negotiated, whereas you get advantage in terms of hardware and speed and everything. These are the references.
Yeah, thanks for the presentation. So I have a doubt. Google has built a data type called as bfloat16, which goes into the TPU.
Yes.
So that's also of 16 bits, but has similar accuracy as that of 32-bit, if you take the use case.
We have done that bfloat analysis also. It's not exactly the same. It will be reduced by around 3% and 4% in the same application.
Okay.
Yeah.
Thank you.
0, 32,2 and all, or it is in generalized? I mean, I can have number of exponent bits can be changed like that. ES.
Yeah, ES can be configured actually. So
okay, so it's
kind of
reconfigurable.
It can
okay,
configurable.
okay, thank you.
Right now we have, it's for 8,0 and 16,1.
So suppose you have this quire-based technique. That means you're making your accumulator very wide.
Yes.
And if your ML applications are such that you may have many zeros, and then your accumulation need not really need that wide register, right? So do you not think that it will be underutilizing the resource? Right?
So it's not necessarily that all the outputs will be zeros. Right? In that case, the sparsity analysis also can be done actually. Sparsity analysis can be done, but still I'll say if you are taking a large application and if you are doing, if the initial things are only positive numbers, suppose you are having suppose 200 iterations I have to do and 100 iterations are doing only positive accumulations, it might go to a very large number. Then it might come, that second phase you will be doing negative iterations. So it's like 1 plus 2 plus 3, it might be accumulated continuously, right? Then it might be a negative number. So in that case also, suppose you have an accumulator width of 8-bit. You can maximum accumulate up to 256. In case of int, I'll say 256. Suppose you have 100 iterations, and if all the initial iterations are positive numbers, imaginary case I'll say, if it is going to about 256, it will be actually going up to 256 and other values won't be accumulated. That is actually issues. So the zero thing, but still we have taken the value. So for each, we have actually configurations. For 8, 0, POSIT 8, 0, maximum accumulator width should be only 32-bit. So it's n square by 2. If it is a 8, 0 POSIT, n is 8. So n square by 2. That's actually random analysis. It's not a random analysis calculation. We have done an analysis and we have reached it to 8 square by 2. So 64 by 2 will be there. And it is also based on some other calculations like min pos and max pos conditions. So how much is the maximum value which can be accumulated in that particular bit width. So those calculations are also done. With that, we are designing the quire width. So that's n square by 2. And even the floating point, the fixed point after that dot values, the fixed point values, that also matters with the min pos value. It's like 2 into n minus 2. That many bits will be keeping as floating point values like a comma b. So that b part will be 2 into n minus 2 bits. So based on that accumulation we will be doing. And yes, whatever you said is correct, but that we have to do a sparsity analysis on that, and then we'll have to do some network which need not do the accumulation and all those things. But for a general case application, quire will be having n square by 2 width. Yeah.
In your work, have you considered precision, dual precision,
no,
half precision?
Normally in neural network application, single precision is enough. We have taken the golden as single precision only, and dual precision is not required at all. But we have actually done that analysis also, comparisons. It will be also the 64-bit or dual precision will be giving almost equivalent results as 32,2 in POSIT. So it's very similar.
Any resource optimization you have done while designing this Mac?
Which one?
Resource optimization, like cycles optimization and all, have you done?
No, we have not done anything. We have just pipelined the thing when in 32,2 and 16, we have done pipelining of 5-stage pipelining. 8,0 in single stage pipeline itself, we are getting around 140, 150 megahertz. So you have to capture because application is different actually.
Thank you for being very active audience, lot of questions, and of course the speakers will be available both in the session, also outside in the breakout area. Please feel free to catch hold of them and clear your questions. Our next presentation is about fast and robust sense amplifier design for digital in-memory computing. Presenter is Kailash Prasad. Kailash Prasad is a Prime Minister Research Fellow at Indian Institute of Technology, Gandhinagar. He received his BTech degree in Electronics and Communication Engineering from NIT Arunachal Pradesh in 2018. And his research interests include hardware for machine learning, in-memory compute, approximate compute, CAD tool design, and SRAM memory subsystem design. And he is an SRC research scholar and has also been awarded Intel India Research Fellowship in 2020. Over to you.
Yes. Thank you. Audible? Yeah.
Yeah.
So as a topic for my presentation is fast and robust sense amplifier design for digital in-memory computing. So a quick introduction and motivation. Actually, we already had using in many of the presentation, but I will just quickly go through it. So today's computing world is being dominated by AI applications. However, if you want to achieve higher accuracy in this AI application, you require large number of MAC operations to be performed. Along with that, the model size is kept on increasing, right? And deploying such kind of hardwares in the edge applications like smart watches, smart cars and all, it is extremely difficult because these hardwares are bounded by resources, right? And to optimize that, many of the approaches have been proposed in literature like hardware software co-design, and people are talking about quantum computing. People are designing hardware accelerators, right? And one of the approaches is in-memory computing. Just a quick overview of a couple of chips that has been recently proposed in last 3-4 years. What we observe is that the most of the energy in this chip actually goes into accumulation buffer, accumulation buffer, accumulation bank. These are nothing but the SRAM memory unit over there, right? So the most of the energy actually goes into the data movement between the processor and the memory. This problem comes due to the underlying architecture itself, because the architecture itself is von Neumann architecture, right? And we have to send the data to the memory, to the processor, right? And the back and forth of the data movement continuously happen. And to overcome this problem, so what we have to do is we have to cut down the data movement, okay? And this can be done by making our memories more intelligent and to compute where it makes sense or where the data resides, right? The memory which we are talking about over here is SRAM. That's the on-chip memory we are focusing on. And SRAM-based IMC has actually been divided into two parts. One is analog IMC, another one is digital IMC. In digital IMC, we use all the digital periphery, while in analog IMC, we use analog periphery to get the final output or the final operation that has been performed. There are advantages and disadvantages of each of these approaches. Digital in-memory computing, because of the digital nature, supports high precision, while analog IMCs has been shown to be more energy efficient as compared to the digital counterpart. Here we are talking about higher precision, so mostly this work has been focused on digital in-memory computing. So just a quick overview how a digital in-memory computing is being performed. So, so these are the two cells. These are two cells, right? And Q1 and Q2 stores the data. And to perform digital IMC, what we do, we activate two word lines, WL1 and WL2. And then according to the data stored over there, the bit line and the bit line bar will discharge, right? And there are two sense amplifiers, as opposed to single sense amplifier in the normal SRAM array. We will get AND and NOR output. These are the logical computation between the two data stored. Please note that this can be connected to a digital compute logic to perform more complex operations like addition, multiplication, and bank operation. So the key component over here, one of the key component over here, is the sense amplifier itself. So the sense amplifier generally used is the dynamic latch-based comparator. So I've just magnified it over here. Please note that one of the end of the sense amplifier is connected to either bit line or bit line bar. The other end is connected to a reference voltage to distinguish or to get the final output. So just quickly going through the working of the sense amplifier, how does it work, such that it will help us to understand the work better. So initially, bitline and bitline bar are pre-charged to VDD. Then if a difference is created between bitline and bitline bar, what happens? After that, we activate the sense amplifier by activating SAEN signal. And after that, whichever the branch has higher voltage applied to the transistor, either M1 or M2, will result into a higher current flow. In this case, it is the second branch. The Y will go down to 0, and the output will be coming as 1. Right? So this is how the basic sense amplifier works. And when we talk about sense amplifier for in-memory computing, now the thing is, we have two data which are stored in two cells, Q1 and Q2. So the data can be 0, 0, 0, 1, 1, 0, 1, 1. And if you see the 0, 0 and 1, 1 case, the bit line is discharging in 0, 0 case, the bit line bar is not discharging. Similarly, in 1, 1 case, the bit line is discharging, bit line bar is not discharging. So there is no problem for the sense amplifier to differentiate between these two cases. However, if you see the Q1 and Q2, there the bitline and bitline bar both discharges, and if you have a simple the sense amplifier where bitline and bitline bar are directly connected, you won't be able to differentiate between the two states, right? And the output will be incorrect. So there is some kind of asymmetricity that has been required in order to use sense amplifier for in-memory computing operation. So there are three works majorly proposed in the literature. The first one is, which I have already shown, where one end of the sense amplifier is being connected to reference voltage. published in JSCC 19. The second is published in TCAS 1, and where what they do to generate the asymmetricity, one of the transistor, so in this case it is the M1 transistor, they increase the drive strength of this transistor by upsizing the transistor. Okay, so that is one of the way. The third way is, in the previous method, if you increase or upsize the transistor, so what happened, the in-memory computing operation will be performed. However, the read operation will get degraded. The normal read operation will get degraded. So in order to overcome that, what the same authors in the same paper have proposed a reconfigurable sense amplifier, where what they do, they have two paths, one for compute operation and one for read operation, right? What they do in order to optimize area, you can see the reconfigurable sense amplifier has 6 transistors in the lower branch, right? So what they do, they use one asymmetric sense amplifier, the other one is a the reconfigurable sense amplifier, because the reading operation requires only one sense amplifier, right? So the right one will only be used in the reading time, and both the sense amplifier will be used while during the compute operation. So the problem, what are the problem with the existing sense amplifier, right? The first, I'm talking about the reference voltage-based sense amplifier, which was the first work. In that, because both the input of the sense amplifier is not coming from similar kind of source, so that it can be impacted by noise. It won't be a fully differential sense amplifier, and it will result into increased offset voltage, resulting into increased delay. The second problem is you have to generate this reference voltage, right? So the generation of reference voltage will introduce additional knob for nonlinearity in the circuit. So that's the first part. The second problem, which we have identified in the asymmetric or the RSA-based sense amplifier, is what we call as capacitive coupling discharge. So just what does I mean by capacitive coupling discharge? This is a simple capacitor, right? So suppose initially both end of the capacitor is at VDD, right? And I have disconnected it from power supply source, so both nodes are at VDD, but it is a floating node. Then what we do, we make one end of the sense amplifier go down to 0. So what will happen, the other end will go down from VDD to VDD minus delta, depending upon the capacitance of this capacitor. So this is what we call as capacitive coupling. So what happens in this sense amplifier, if you see, this is the asymmetric sense amplifier. One end of one of the transistor is M1, and it has been made asymmetric by upsizing it, right? So what will happen, so initially both the end of the, both M1 and M2 is connected to VDD. Then we will activate the sense amplifier by activating SIN signal. Then the node between M1 and M2 will go down to 0. And after that, what will happen, because of this, because of this capacitive coupling, the bitline and bitline bar will further discharge, right? And please note that why it is happening, because this M1 and M2 are large transistors over here, okay? And the CGs of these transistors is making them discharge. And I have written delta V1 and delta V2. Why? Because both the transistors are not of same size. Because of the asymmetricity we have to generate, we have made them of different size, and because of that, what happens, the difference between the bitline and bitline bar is being created, okay? And this actually result, so this is the value, the plot which I am showing over here is just for the single simulation, right? In the Monte Carlo simulation, we observe around 100 millivolt of difference that has been created between the two nodes. So what is the solution for that? Okay, so just before that, this is the ASA-RSA pair which the authors have proposed, and you see the bitline and the bitline bar is seeing different capacitance because it is connected with the different logic, and because of that, the bitline and bitline bar will discharge differently, and it will result into failure. And which we have performed 2000 point Monte Carlo simulation in CMOS 28 nanometer, and we observed that that there are failures in that. So the straightaway solution is to make both the bitline and bitline bar see same capacitance, right? And how we can do that? We use same kind of sense amplifier at both the end. So we have done that, and we call this as modified RSA sense amplifier, MRSA. One of the things which we had to do, because in CMOS 28MR, we were not able to generate asymmetricity over there, so we have to use ultra high VT and ultra low VT transistor. So in the read mode, how it works, so what you have to do, you have to turn off the compute signal, activate the read signal. So in the read mode, it will behave like a normal sense amplifier. In the compute mode, you have to deactivate the read signal and activate the compute signal. So the other path will be activated. It will be behaving like a sense amplifier for the compute operation, right? And we have performed 2000-point Monte Carlo simulation. You observe that there is no failure in both AND and NOR operation. Further, if you see the previous sense amplifier, there are 6 transistors over there. So it is 4 more extra transistors and 4 heavy transistors. And along with that, there are LVT and HVT, ultra low VT and ultra high HVT transistor. What it does, it increases the area of the sense amplifier. Along with that, the energy consumption and the latency is high for that. So for that, we have proposed a CESA sense amplifier. We call this as compute enabled sense amplifier, where we just use 1 extra transistor, and it is connected with a compute signal. So whenever a compute operation will be done, this signal will be activated. And in that regards, this sense amplifier has very less area, lesser energy, and lesser latency as compared to our previous proposal. And if you just see in the read mode, how does it work? So that we will deactivate this M3 transistor. And you see the bitline and bitline bar sees the same capacitance. There won't be problem with the capacitive coupling discharge. In the compute mode, what we will do, we will activate this M3 transistor. What will happen, that there will be asymmetricity generated between M2 and M1 and M3, right? So M1 and M3 will activate in parallel. So we have performed again 2000-point Monte Carlo, and we observed that there are no failures in both the proposals. So we have compared our design, the CESA design with the MRSA. We couldn't compare with the existing design because the designs were failing under process variation. And what we observed, the proposed CESA has lesser offset voltage as compared to MRSA, and the delay improvement for both read and compute operation is around 20.4% and 16.45%. And energy per bit has also been reduced by 5.9% and 55.87% for compute and the read operation. So we have compared our design with the existing literature. For comparing, what we have done, we have implemented a 16 kV SRAM array, 128 cross 128. We have integrated all the peripherals. We have also integrated the compute circuit, and we have performed 8-bit addition in our proposed IMC with the proposed sense amplifier. And we observed that our proposed architecture works at 1.43 gigahertz. Along with that, the energy, the TOPS per watt per bit is 56 TOPS per watt per bit. So just to summarize, we have analyzed all the existing sense amplifier literature, and we have shown you what are the problems in all the existing design. We have proposed the first solution that is called as MRSA, right, by modifying the existing sense amplifier. Then we have proposed the CESA sense amplifier, and the CESA sense amplifier improves the compute access time and energy by 20.4% and 5.95%, and the read access time and energy by 16.67% and 15.85% compared to our own MRSA proposal. And when we have integrated this in complete in-memory computing solution with the compute circuit, the whole IMC architecture works at 1.43 gigahertz and has energy efficiency of 56 TOPS per watt per bit for the addition operation. So that's all. Thank you. If you have a question, feel free to ask.
PVT variations, like to check against.
Okay. So this is Cadence ADXL. So this is the spectral simulation we do.
Okay. Yeah. And what is the bit error rate for your Monte Carlo analysis?
So the bit error rate for the SRAM you're talking about?
Yeah, when you check your design, that is the sense amplifier.
Yes, so the sense amplifier doesn't give you the error we have shown.
Yeah, how do you come to the conclusion that the bit error rate is reasonable? Like, I'm just curious.
So we have performed Monte Carlo simulation. So
Yeah,
we have performed, so we have shown the result of 2,000 Monte Carlo simulation, but we have gone up to 10,000 and 15,000 Monte Carlo simulation in order to verify that there is no error, whatever we are reporting over there. Yeah.
Okay, and one last question. Is this sense amplifier applicable for other in-memory platforms like resistive RAMs and others?
So generally, this sense amplifier is applicable where we have both bitline and bitline bar. So the proposed sense amplifier. So wherever in any of the solution, if you have two differential signal which is coming, this sense amplifier is applicable for that.
Thank you.
Yeah.
How did you got that number and which technology?
That is TOPS per watt per bit. Yeah.
TOPS per watt per bit. So
yes.
how did you calculate it?
The TOPS per watt per bit. So we have performed the 8-bit addition operation, and then we have calculated the energy. We see that per second, how many operation we can perform, how many 1-bit addition we can perform, and then for that particular operation, what is the power you are getting, and just by dividing that, we will get the metric. Sorry? It is CMOS 28 nanometer. Yeah. Any more questions?
If I'm not wrong, through your slides, you show AND gate or one more gate like.
Yes.
So those are the computations you are.
Okay, so we support logical operation, which I have shown AND and NOR. Then after that, we support addition operation, and the final result has been presented for addition operation. But apart from that, because we support bit serial arithmetic, we can go for multiplication. Along with that, we can also go for MAC operation.
Okay. And can you move to the slide 24? But you also have all PVT variations and all.
Sorry?
You incorporated the process variations.
Yes, definitely, right.
So this is, you are saying this star, this work,
TCAS one work.
Okay,
yeah.
that fell under the process variation.
That fails under the process variation.
Fine, good, okay. That's all.
Okay. Just to add to the point, we have sent this design for chip fabrication. So we have done the layout and everything. So we'll be receiving the chip in, say, next 4 months, and we will have the chip result also. Yeah. Okay.
This one. Okay. So the sense amplifier for normal operation.
Yes.
That also has an asymmetricity, isn't it?
Sorry?
That has a at the output node. I mean, there is asymmetric capacitance. The capacitance is not balanced, isn't it? In both the wings of the sense amplifier for normal operation also.
It is balanced.
Normal read operation.
It is balanced actually. It is actually balanced for both normal read.
How?
You can see for normal read operation, M1 and M2 is there. So both M1 and M2 is of same size, and the M3 transistor is
capacitance. The drain capacitance of M1 and M2 would add, whereas for M2 it would. There is a difference in the capacitance, isn't it?
You're talking about the drain. So actually the CGD was not creating the problem. The problem was with the CGS. Because what happens as soon as you activate SAEN, the first, the node which is between M1, M3 and M2, the common node that is been sharing, that goes to 0. And because of that, bitline and bitline bar pulls down. So that was the problem. So we have to make sure that the CGS of both the node remains the same. So bitline and bitline bar is seeing the same CGS, and I think it is also seeing the same CGD.
Yeah, but okay, the parasitic capacitance at M1, M3's drain.
So that is not the problem. The parasitic capacitance associated with bitline and bitline bar, yeah, that is the.
But would it not make the difference in the bitline bar that you want? Would it not change it for the sensing operation?
I believe it won't change it because So why should it change it? So that's my point. Yeah.
Okay.
So the CGS remains the same. CGD also remain the same. I understand what you are saying, that at that particular node, so there is an extra transistor which we have connected, right?
So
because of that, there might be some capacitance,
right,
and that will be extremely negligible as compared to the coupling capacitance.
Okay.
Yeah.
M2 and M3, if you can comment on that.
Okay, so M1 is, so if the minimum width of our technology is W, so M1 is 8W, and M2 is also 8W, and the M3 is 2W.
Okay. Okay, fine. Thank you.
Yeah.
Okay, so the next presentation is MOSCON, Modified Outer Product-Based Sparse Matrix Multiplication Accelerator with Configurable Tiles. And the presenter is Nobel G. Okay, so Nobel G is a PhD scholar at Department of ECE, Indian Institute of Information Technology, Kottayam, Kerala. His research interests are VLSI and FPGA-based system design, hardware accelerators, and associated design methodologies. Over to you, Nobel.
Good afternoon. Myself, Nobel G, doing my research in Indian Institute of Information Technology, Kottayam. And my topic is MOSCON, Modified Outer Product-Based Sparse Matrix-to-Matrix Multiplication Accelerator with Configurable Tile. And my co-authors are Naleshis and Kalayas. So these are the agenda for today's presentation. We will start with an overview, related works, motivation. Then we'll go to the proposed architecture. We named it as MOSCON. Corresponding FPGA implementation and result, conclusion, and a reference. So as you know, a matrix which contain majority of the elements are zero are called sparse matrix. And sparse matrices are commonly used in machine learning, especially you can see natural language processing and robotic vision, graph analytics, online platforms, etc. So there we are using something huge matrices, and these matrices size are something is very large. So representing it in normal format like row value, column value, then corresponding value, it is going to consume a lot of memory. And that's why we are having some special representation. Lot of representations are there to represent sparse matrix. And very commonly, we are using two representation, and it is known as CSR and CSC representation, compressed sparse row and compressed sparse column format. So machine learning architecture, they demand high performance sparse matrix to matrix architecture, multiplication architectures. We are proposing an accelerator for the same. Okay, so an accelerator which is in hardware and which can be implemented in FPGA. So let us go quickly to the related work. So we have tabulated, we have listed all the existing state-of-the-art sparse matrix-to-matrix architecture here. There are a lot of different algorithms are there, and majority of them are using outer product algorithm. Okay, so outer product-based sparse matrix multiplication, and we are also following the same thing. And let us go to the motivation. And from the literature review, we identified few limitations for the existing architecture. So we have listed here the limitations that we identified. It is like first problem that we identified is some load unbalancing issue. Since we are dealing with a sparse matrix and it is having different number of elements in each row. Okay, so when we are considering about a tile arrangement, the number of elements that allocate into a particular tile, that will be different in each tile. Okay, so in sometimes some of the tile may be allocated completely, and sometimes it may be like it may allocate partially. So this may create some load unbalancing in the architecture. So that problem that we need to rectify. And the second problem or second limitation that we identified is some partial product. So during the matrix multiplication, definitely partial product will be there, but we think that it is possible to reduce that partial product in some extent. Okay. And the next one, it was configurability. In majority of the architecture, they are using, it is statically binded, like different rows are allotted to the same number of processing unit. So some type of configurability that will help to improve the performance. And the last one, we require some sorting mechanism. And some parallel sorting mechanism, definitely it is going to improve the performance of the architecture. Okay, so that's why from these limitations, to overcome these limitations, we are proposing our architecture. It is based on it is a modified outer product architecture, and we have given a name MOSCON. And these are the contributions for our work. It is a modified outer product based sparse matrix to matrix multiplication with load balancing. Then we can do the multiplication of any sparse matrices with any dimension with less number of partial product. And we introduce configurable tile with bitonic sorting. That means whatever limitations that we discussed in the previous slide, we just find out some solutions for that, and we implemented our architecture. Let us go to the architecture, MOSCON architecture. So MOSCON means, as I said in the title slide, it is modified outer product based sparse matrix to matrix multiplication accelerator with configurable tile. So the corresponding overall architecture I have listed in this slide. Since it is a matrix to matrix multiplication, we require two matrices A and B. So one will be in CR format and another one will be in CC format. So it is shown there in the slide in the architecture. And we will fetch the elements into the memory. So there will be, we require a fetch unit. Then we will go to the sparsity checking. Okay, sparsity checking and element parsing, another section. And after that, it will be given to the tile arrangement, tile unit. So there it is actually, all the processing is going to happen in that tile. So we are using 16 tile in this architecture, and each tile is having 8 processing elements. And from the tile, we are going to get partial product, and that partial product needs to be, we need to do some operations, like it is done by partial product management. We have listed 3 things. We need to do partial product storing, then we need to sort it, and we need to merge it. And finally, we are going to get the answer. Okay, so this is the overall architecture of our MOSCON, and we will go to each individual unit separately. Okay, so let us go to the first one. It is fetch unit. So it will fetch the elements, and since we are using CSR and CSU representation, we can say that if you compare starting address with the ending address, you can identify the sparsity. Okay, if they are not equal, that means that particular row is having some number of elements. Okay, so we are using a comparator, and it will compare, and if they are not equal, we will set the corresponding valid bit to a high. And only the rows or columns with valid bit having a high value will be proceeded to the next stage. Okay. Next unit, it was sparsity checking unit. And in previous unit, we will fetch it at the same time, we will check the sparsity of the matrix. And now what here this unit will do is, it will check the sparsity among the 2 matrices. Okay, that means when checking a row and column, there are 3 options can be there. Either it can be equal, or it can be less than, or it can be greater than. Okay, if a row and column are equal, that means it is good. It is not sparse. We can proceed those elements to the next stage. So corresponding valid bit, you can see there, that valid bit we will set to the high value. So it will check the sparsity among the 2 matrices, this particular unit. Next is tile allocation. As I told in the first, in the overall architecture, I have shown 16 tiles there. Okay, so corresponding 1 tile I have shown here, it is tile 1, and we are using 16 tiles like this. And in this tile, we are using 8 processing elements. Okay, and again, these processing elements are, we have combined. We made a concept called subtile. So these processing elements are arranged like 5 subtile. And 3 subtile which contain 2 processing element and 2 other subtile with 1 processing element. So thing is like, according to our requirement, according to the number of elements in this row, we can combine the subtile. Okay, so the different combinations are possible, and that will be defined by the configuration B. Okay, so for example, if a row is having 3 number of element, I can compare subtile 2 and subtile 1. Okay, if it is 8 number of element, I can compare NDL subtile. So same tile can be allotted for different number of rows. That is also an advantage. And this one is going to be the partial product management, and it consists of 3 things. Tiles will generate some partial product, and that needs to be stored into some linked list, and it will be sorted, and we will take each element from the sorted list, and we will merge it to generate the final output. So 3 operations will be done by this particular partial product unit. So now let us go to the corresponding implementation and result. So we compared our architecture with existing stage of the other works. So our architecture is MOS-cone. So you can see outer space, Spark, Sexton, Spaghetti, Matrator, Gamma. There are other sparse matrix to matrix architecture implementations. They are the implementations. And we compared our architecture in terms of different algorithm use, corresponding data condensing, sparsity, whether they considered sparsity, and how they are generating input submatrices, etc., just a comparison table. And the next one is corresponding FPGA implementation. We have implemented our architecture in Kintex 7 FPGA with 32-bit single precision floating point format. And we have executed some benchmark dataset from University of Florida, suits parts of data collection. And we observed a performance improvement of around 9.21% with respect to the stage of that implementation, MOS-cone. Okay, so corresponding result we have listed in this table, and the corresponding hardware utilization of both architecture we have listed in the second table. So conclusion, we modified outer space implementation with improved performance, and the optimized architecture for performing sparse matrix multiplication with less number of partial product. It will do some reconfigurability, it will support a reconfigurability. Then load balance architecture, and it is using some improved parallel sorting algorithm, and we observed an improvement in performance by around 9%. And these are the major paper that we refer. Thank you.
Actually, you are doing the sparsity analysis and you are skipping or you are getting the zeros?
No, I am not doing sparsity analysis. Already the benchmark data sets are available for sparse matrices. So I will take those metrics and I will do the multiplication. And it will be like, in terms of machine learning architecture, we are using huge matrices. And for implementing that multiplication, we are proposing an architecture.
No, you said, right, because during the number of zeros will be more in that convolution layer, so you are going to skip, you are going to remove that operation, right?
We are making an optimized architecture for the multiplication. We are not optimized architecture for the multiplication. Yes, that's the thing. We are not considering 0. Yeah, we are removing the 0.
You are
yeah, it is according to the representation. Yeah, we are removing the 0.
You are removing the 0 because you are. That's why I'm asking. You are removing the 0, or
at the beginning. We are not making those instructions, those zeros into the architecture level.
Okay,
so that means if I included zeros, it will just do the operations with 0. We know that multiplying 0 with something, it is going to be 0.
Yes.
So we are not doing some times on that particular thing. That's the thing.
Yeah, so during that time, your multiplication will be ideal state, right?
No, it will multiply other thing. We will avoid the 0 conditions. We will not consider zero values. So zero values will be avoided at the beginning stage. We are having some sparsity checking section.
Okay.
So there itself, I will filter out those zero value.
Yeah, okay.
Then whatever remaining, it is going to be only actual value. So
Okay.
those values are only going to generate the meaningful result.
Okay.
And so I'm considering those values and will do the remaining operation.
So, okay, if suppose you are going for the convolution layer, like those things, it is a 3x3 matrix will be there, it is stride will be there. Again, if you are going for this another matrix 3x3s, 1 by 1 like that, there is a load imbalancing will come, right? Load imbalancing, it will come, right?
We are considering about huge matrices, very huge matrices. And we are, as you can see in this architecture, like the number of elements, it is going to be around 1 lakh. It is that much huge matrices we are dealing with. And in between those two matrices, we are not considering about the sparsity will be like, if I am saying about sparsity, if I have 1 lakh entry, out of 4 or 5 elements may be something huge. We are not considering about small matrices. In terms of small matrices, this architecture is not good.
Okay.
It is not. We can go with generic matrix multiplication. That is going to be good.
Okay.
For huge matrices, this architecture will be much efficient.
Okay. Okay, thank you.
Noble, a question here.
Yeah.
First of all, pretty close to my heart.
Okay.
Question. You have only shown the performance gain.
Yeah.
Performance gain without saying a single word about the power or energy doesn't stand much meaning. So could you also, if you have, could you also say about how your scheme was doing in terms of energy or power?
Sir, architecture is good in terms of power also. I think we have included that result in my paper also. We have included that result, power analysis. It is good comparatively. Compared to other architecture, we have slight increase. It is there in terms of power because we are doing some external, some extra logic we are including. So definitely we are having slight increase in power as well as in area, even in resource utilization we are seeing. But we are thinking that it is an accelerator. And for an accelerator, we think that we are considering that the performance is the much thing. Okay. So with an overhead of power and area, it is there.
Yeah, I would like to see it, but I take it on the face value. Even if it is, say, so-called slight, it depends on how many times and how large you do such calculation. It could be a linear complexity in terms of your energy efficiency. So if you have a one size of so-called large matrix, if I double it, triple it, or if I exponentially grow the matrix size, I would like to see that slight increase in power, how does it goes in your scheme. So perhaps that is something you can look into it.
Yes, definitely, sir. We will look.
And another fundamental question, why you are trying to do it at a hardware level, where people are even suggesting you could eliminate the sparsity at a system level, at a higher abstracted level. If that's something you can think of, and then you can still make a comparison, how your scheme, hardware will always be fast, we know it, right? But there are challenging solutions at a system level, which are unfortunately efficient. Perhaps if you can show that your scheme still is better, even in one parameter, that would be good to see.
Okay. Sir, we tried for a complete hardware simulation, hardware accelerator. So in that way we approach. Okay.
So Noble, just as an extension, a PPA table would be nice. So power, performance area, I mean, I can see the slice registers, the overall slice LUTs, they're all definitely more than the outer space solution, right? And let's say the performance was 20%, 30%, for a slight increase in resource usage, then lot of merit goes to the MOSCON solution. So right now, the average is about 9%, and if I just take slice registers, you're already using more than 10% of slice registers. Right, so a PPA table.
Okay, definitely, sir. We'll try it in the next slide.
Yeah, one question here. Here, look into the paper. The second question is will it work for sparse dense or only sparse?
It is dense.
With the two metrics you have.
Yeah.
So one matrix is sparse, if other matrix need to be sparse?
Both metrics can be sparse.
Can be sparse or should be sparse?
No, nothing. It is, if it is sparse, this architecture will perform extremely good. And if it is dense, the architecture will take, it is not that much good. We are considering about sparse matrix to matrix multiplication.
So both metrics should be sparse?
Yeah, that is some good thing.
Okay. And any comment about complexity, time complexity or algorithmic complexity?
So time complexity, it's depending upon the number of dense or sparse metrics. So if I give some dense metrics into this particular architecture, definitely it is going to take a lot of time.
No, any comparison with the existing work, how complex it is? Or
so we compared like this way.
We're getting time advantages, I agree, but depending on the area or overhead, complexity analysis?
We compared in terms of performance and area. And power, it is already there in the paper. And
okay, fine.
That's
So actually one question. Yeah. Okay.
You said authors are available.
On sensors and wireline will start now. So I am Arup Polle from IISc Bangalore, and I have with me Abhishek Srivastava from IIIT Hyderabad. So we'll be chairing this session. The first talk will be on invited talk. It is on millimeter wave sensing and low phase noise VCOs. So a brief intro for the speaker. Professor Abhishek Srivastava is a faculty member at the Center for VLSI Design and Embedded Systems Technology, IIIT Hyderabad. He received his PhD in electrical engineering from IIT Bombay. He was a postdoctoral researcher at Electrical and Computer Science Engineering Department at Purdue University, where he worked on fully monolithic millimeter wave oscillator. He is a senior IEEE member. His research includes RF and analog integrated circuits and systems for wireless, sensor-based connected healthcare, high-performance millimeter wave communication, and sensing applications. So welcome the speaker.
Thank you, Professor Arup, for introducing me. First of all, I would like to thank the organizer to giving me this opportunity to present my work in this conference. So in this talk, basically, I'll be touching upon various applications of millimeter wave sensing, what our group is doing here, and one design that we have recently done, which my group has recently done on a low phase noise VCO. So I come from IIIT Hyderabad and a part of Center for VLSI and Embedded Systems Technologies. So we have a very good group there. We are 5 faculty members there. So if any one of you are interested to know more about our works, feel free to connect to us, visit our web page, and we work in almost all domains of VLSI and embedded systems, circuit design, AI/ML related circuits, IoT embedded systems. So feel free to visit and connect us over email. And we are also actively looking for MS and PhD students in our center. So if you are interested, feel free to connect to us. So in this talk, basically, I would like to touch upon millimeter wave technologies, its applications, and why the VCO and specifically low phase noise VCO is important. And one of the aspects of design, how to achieve low phase noise, what my team has done, will be discussed. So earlier, when we talk about millimeter wave, it look like it's only for, for theory. It will not happen in reality. But as of now, you know that many of the real world products, such as Qualcomm's Snapdragon, which is having a modem at 30 gigahertz frequency, is out in the market. And it's being used in many devices. Apple also, from its iPhone 12 model onwards, is giving 5G connectivity, physical connectivity at 30 gigahertz, and it's there in the market. And whole, motivation here is to get more and more bandwidth, and more bandwidth is possible with more and more at higher carrier frequency. And to have higher bandwidth, you will have to aggregate bandwidth over multiple channels. So for that, you will need to have MIMO kind of systems. So that is one aspect of millimeter wave. The other aspect is usage of millimeter wave in radar technologies. Here I am taking on a specific example of frequency modulated continuous wave radar technology. So this has found its use in various applications such as autonomous driving and parking, healthcare application, object detection in poor weather conditions and all. So what is this FMCW technique? So essentially you have a transceiver where you feed a signal which is called a frequency chirp, as shown in this bottom diagram. So you transmit this frequency chirp. So frequency chirp is starting from frequency f0 with some bandwidth, say f0 2 plus delta f. It will be sent towards a target. It will hit the target and return back. And then you mix up the transmitted and received signal, and you find the intermediate frequency after mixing. So with that intermediate frequency IF, the value of the frequency and the phase of the frequency, you can extract many information, such as the range, distance of the object, say in vital monitoring, health care application, you can even sense what is the chest wall movement rate, hence heart rate and breath rate. Many information can be extracted from there. So this millimeter wave technology or the carrier, whether it is communication purpose or sensing radar purpose, it has some key requirements which are like you need to have higher chirp bandwidth. You need to have your chirp should vary from for a large bandwidth. Because if you see this formula written down here, if you want to resolve finer ranges, you will need to have higher bandwidths. And similarly, you will need to have high linearity in your VCO. High linearity as in when you switch from one frequency to another frequency, the frequency shift should be linear. Okay, so basically K VCO, gain of the VCO should be as much low as possible. And of course, low phase noise is a key requirement. And other thing is you would like to have complete chip solution for reduced bill of material and portability. So there are some examples which we tried out at our lab. So my student, Joel, he developed one health monitoring prototype using TI's IWR radar board for measuring breath rate and health rate. It has its application. You can say that already we have multiple, devices. Why do we need it? So you can think of a scenario where if you want to do mass measurement in a pandemic-like situation, you don't want non-contact, basically you want measurements, there it is highly helpful. This is the other work that my students Shayan and Aditya carried out. So using the same radar, they are able to find the ranges, identify the what type of objects it is there, which has its usage in ADS applications. So now moving towards the millimeter wave carrier generation approaches. So we have application requiring millimeter wave carriers, some requirements, low phase noise carriers, how to generate that. So typically we can use a PLL where a VCO is kept in a loop and then you generate the required frequency. So there are some pros and cons for this method. For example, if you suppose, take the scenario, first slide we saw MIMO kind of condition where you, suppose you have 64 cross 64 kind of array. And you want to have one source which will route clocks for all these transceivers. So what will happen? You will end up in burning a lot of routing power. And of course, the phases which are reaching towards each transceiver, you'll have less control. There are ways, methods with which you can correct the phases, but again, you'll have to spend some money on it. So what could be the alternative approach? So we can go for local RF carrier for each transceiver. But if we go with this approach, where the reference is typically a crystal oscillator, we'll have a crystal which will be a bulky in size. We cannot, again, have 64 cross 64 crystals on a board. That will not be very lucrative solution. So other recent happening is this CMOS MEMS hybrid approach, PLLS. So what people are trying to do, they are trying to create high frequency resonators, millimeter wave resonators, high quality factor resonators, which you can directly use to build oscillators. So some works have been reported. For example, this 30 gigahertz resonant FinFET based resonator has been reported. And using these, it is possible to build high frequency direct wave carrier generators. However, they have their own challenges, which you have to overcome. But this is one of the directions where one can work. So whether this is approach 1 or 2, as far as phase noise is concerned, the phase noise is, we can say that it is proportional to noise factor of the circuit and inversely proportional to square of the quality factor of the tank. And in another approach where Hajimiri presented a very beautiful theory for phase noise analysis, we also know that phase noise is directly proportional to the RMS of impulse sensitivity function of the waveform. So impulse sensitivity function basically describes how sensitive is your waveform if the noise is injected at different instances of time. And based on that, you can kind of estimate what is the phase noise of your system. So the major approaches for low phase noise design, which has been reported in literature in past few years, people are trying to reduce noise factor F, which has reached to its theoretical minimum now. And they are coming up with innovative inductor design for increased quality factor. And third approach is to reduce the RMS value of the ISF. So based on the third approach, we have done some work here for low phase noise oscillator design, which I'm going to show here. So it has been shown that so the picture here on the bottom shows a typical conventional cross-coupled LC oscillator with the major noise sources. It is shown that if we use a transformer as a tank instead of simple LC resonator, we can have two resonant frequencies. So if you see the model of electrical equivalent of the transformer, which is shown on the right side, and do network analysis, you will write the transfer function, you will find that there are possibility of two resonant frequencies, which can be tuned by properly choosing the sizes of these primary and secondary side capacitor and inductors. So what essentially will happen if you have multiple harmonics in your system, it will not be a pure sinusoid. It will have multiple, you can call this as pseudo-sinusoid. So what is the benefit of having pseudo-sinusoid? So as shown here in the bottom graph, the pure sinusoid has an ISF impulse density function, which also looks like a sinusoid. This is a pseudo-sinusoid, or say squarish wave. Its ISF function tau omega t is shown to have in this impulse kind of response. So if you take RMS of this as compared to a typical sine wave, you will end up in having low RMS ISF. So idea here is to have a transformer tank to generate pseudo-sinusoid waveform, which will give you impulse sensitivity function with lower RMS value, which will help you in reducing phase noise. So that is the idea. So using that, we have done this simple design, and then some math was done to identify the values of the primary and secondary side of the inductors. And I think I'm running out of time. So yeah, so basically we did some math and then found out that using smaller inductor with less than 1 turn, we can get higher quality factor in tank and have lower phase noise. So using this, we completed our design. And these are some post-layout simulation results, which shows that we could achieve about PN of minus 117 dBc per hertz at 1 megahertz offset, around 19 gigahertz frequency. And as compared to other works, of course, our work is simulated, but it shows some promise. We'll be taping it out soon. Yeah. So yeah. So finally, to conclude, that there is an increasing demand for low phase noise wave VCOs. Lot of interesting work are happening and can be done in this area. And finally, I would like to acknowledge SERV for funding this research, and iHub Mobility, IIIT Hyderabad for giving us experimental benchmarking space. Thank you.
For Professor Sriwastava. So the next speaker is Anamika Sharma, and the title of the paper is A Portable Ultra Low Cost Multi-Gas Sensing System on Module for Wireless Air Quality Monitoring Network. So Anamika is a PhD student at IIT Bombay since 2019. She worked on high-speed digital to analog converters. Presently, she is doing research internship at ST Microelectronics at Greater Noida. She did her BTech in EC from NIT Tiruchirappalli in 2016. She did MTech in Electronic Systems from IIT Bombay in 2019. Her research interests are analog and mixed signal IC design. She has recently received SSCS Student Travel Grant Award for attending ISSCC 2023.
Thank you for the introduction, sir. My name is Anamika, and I'm here to present my work on a portable, ultra-low-cost, multi-gas sensing system on module for wireless air quality monitoring network. Here is the brief agenda of my presentation. I will start with the brief background on air pollution, the motivation behind our work, the system architecture, and its key features as low-cost sensing, the data analytics, and the power consumption profile. I'll conclude with the conclusion. Air pollution is a global problem. It is the presence of unwanted chemicals and particles in the atmosphere because of the human activities and industrial activities. Air pollution has adverse impact on the environment and human health. It results in the reduced life expectancy. The conventional method of monitoring air pollution are using standard pollution monitoring stations. Here on the left is one such situated in our campus at IIT Bombay. These monitoring stations involve huge installation cost, and because of that they are scarcely located and they require manual intervention for its operations and management. This was the motivation behind our work to develop a low-cost and portable air quality monitoring device which will require minimum human intervention and hence can be densely deployed to supplement the air quality monitoring along with the standard pollution monitoring station. And with the results from these devices, we can identify the key hotspots where air pollution is more, and the relevant authority can then take control measures to control the air pollution in those areas. The presented work is a part of the project Satvam, which had 3 research vectors: low-cost sensing, energy harvesting, and data analytics. Our team at IIT Bombay was specifically involved in low-cost sensing, and that work will be presented today. This is the system architecture of the proposed sensing module, which consists of gas sensors, its analog front end, a microcontroller for data acquisition, and transceiver for data transmission. The gas sensor forms a key element of a gas sensing system. Of the types of gas sensors available in the market, that is electrochemical gas sensors and the MOS type gas sensors, we choose electrochemical gas sensors. They are suitable for ambient air quality monitoring because of its properties to detect the gas levels in parts per billions and as well as their low power requirements. We have, in our module, we support the measurement of nitrogen dioxide and ozone along with PM measuring. The electrochemical gas sensors require analog front end for measuring the gas, which consists of a potentiostat and a transimpedance amplifier. The next key element is a microcontroller unit, which is responsible for data acquisition and data transmission. If we look at the conventional products or in the literature, they mainly use a Bluetooth module, a Wi-Fi module, or a Zigbee module, which works at 2.4 gigahertz spectrum, which is dominantly used and is its congested spectrum. So we propose to use the sub 1 gigahertz spectrum for our application, and its key benefit, the key benefit it provides is its long range of communication at low cost of development and low power consumption. As we propose an integrated solution, it was key to identify an integrated IC which provides us both the functionality for data acquisition and transmission. So TI's CC1310 was found out to be suitable for our purpose. Each monitoring device can communicate to a host node. The host node consists of a similar 1 gigahertz, sub 1 gigahertz transceiver and a Raspberry Pi. It is responsible for collecting the data from various gas sensing nodes, storing locally, and then transmitting it to the cloud for data analytics. Here on the slide is the brief journey towards, from the beginning towards development of the final multi-gas sensing system on module. We started with gas sensors and a module called as Zolertia remote, which has two separate ICs for acquisition and transmission. In the version 1.1, we added a temperature and humidity module, as the electrochemical gas sensors, its performance are quite sensitive to the temperature and humidity. And the version 1.1 was also deployed at two different locations, one at MRIU Faridabad and one at Mumbai, for calibration against the reference, standard reference analyzers. And once we confirmed the performance of the electrochemical gas sensors, our goal was to minimize its cost. For that, we replaced the Zolertia module with the integrated microcontroller CC1310. And jumper wires running from one here to there to microcontroller to the power management ICs made it less reliable and susceptible to noise. And for that, we developed a PCB in-house, and that is our final product. So we propose an integrated solution for air pollution monitoring, which consists of this sensor conditioning circuitry, the microcontroller, and the transceiver, along with the power management circuit. This module acts as a plug and play. All we need to do is connect the power and the gas sensors, and it'll start transmitting to the host node. The key features are its low cost of development at less than 20,000 INR, low power consumption, it's very compact in area, and hence portable. As no jumper wires are used, it's more robust and reliable. Additional features include onboard antenna and USB compatibility. So this is how the final product looks like, with 3D printed enclosure and C-shaped slider fitting for opening purpose. Its dimension are 15 by 10 by 5 centimeter. Just for the reference, the mug is placed beside our device to show the compactness of the final product. So once the hardware is ready, these low-cost sensors are not that accurate as compared to the standard devices. So these need to be backed up with the data analytics, and at the ground level or at the module level, data cleanup and data averaging is performed, and then these are transmitted to the host node, where the further processing takes place, basically converting the raw data into the PPB values, and further computational models are applied to obtain reliable, accurate results. Thanks to the team at IISc Bangalore, data analytics was performed by them, and the results can be found in the reference papers. So the sensors and MCU were found out to consume less power, but then the PM sensor was consuming significant amount of power, and hence its operation was duty cycled in order to control and reduce the power consumption by the PM sensor. So in conclusion, we propose an integrated solution for air quality monitoring purpose, which can complement the standard pollution monitors for real-time air quality monitoring. Its key features are its ultra-low cost, low power consumption, small form factor, it's scalable to add more sensors, and because of its wireless connectivity, it can form an IoT network, and it provides real-time monitoring.
Anamika, first of all, I'm really pleased to see such a product, and a special thanks, and in fact, a round of applause for them. Such products are required for our ecosystem.
Yes.
So I'm very pleased that somebody has finally made it. Few remarks. I think I would like to see, instead of 20K, perhaps make it in 2K. That would be first thing. Second remark is, could you also see if you could also check the viral content in the environment by adding another type of sensor? And I think everybody will agree that that is also an apt thing to do.
Yes.
And I also saw the data mining. I think you can still use the cheapest filter, if I may say so, but perhaps then you make a grid, assuming that you will even drop down the cost to even 200 rupees. You can throw out the Raspberry Pi. There are methods, because your complexity is not that big.
Yes.
So I don't think you need a 5K or 2.5K Raspberry Pi or microcontroller. You can do it with the cheapest IC. I'm sure if you do a little bit more work, you can bring it to 2.0 reduction. Then you can make a grid. And with the grid, if you take an average data mining algorithm, you can have a very accurate result. Thank you
for your suggestion, sir. We'll take care of it.
Thank you. So Anamika, the 20K to 2K, I think is a good step forward. So I was wondering, maybe I missed part of the stuff. So in terms of accuracy compared to what we currently have in the industry versus this one, you mentioned you have to calibrate. How far are we? Are we like within 5% or? So can you give me a number? So if I compare this with what's commercially available.
So what I can tell you is on performing a very simple linear regression on these modules, we could obtain the R value of close to 0.8 to 0.9. Yes.
Thank you.
Thank you.
Just one, I could not see that how much is okay, here I missed it. Okay, then I got it. Thanks.
Thank you. So just one remark that we are limited actually right now, we are limited by the cost of the gas sensor. So some amount of the gas sensor. So from the electronic side, we have tried to minimize the cost. The limiting factor are the gas sensors at present. Yes. Thank you. Thank you.
Thank you.
All right, so the next paper title is FPGA-based smart and sustainable agriculture. The authors are Perakashyam, Irfan S.K. Ali, Durga Basu Mogili, Ashok Kumar Palivela, Sudhir Reddy, Jyotsna Bhavisetti, and Dhanush Reddy Y. The presenter is Dhanush Reddy. Yes. Okay, so he is currently pursuing engineering in third year at Department of Electronics and Communication Engineering, Rajiv Gandhi University of Knowledge and Technologies, Nuzvid, Andhra Pradesh. He is working as an intern in Sense Semiconductors and IT Solutions Private Limited, and he is experienced in FPGA-based designs and ASIC design. His team won Silver Award in the Innovate FPGA Design Contest 2022, which was organized by TerraSIC, Microsoft, and Intel. And his current research areas of research is implementation of technology in the field of agriculture. So welcome, Dhanush.
Good evening, everyone. So I'm Dhanush. So coming to our project. So our project title is Smart and Sustainable Agriculture using FPGA. So this is overall agenda of my presentation. So let's directly move into the overview. So our this is our central theme of our project. So our project mainly focuses on crop customized irrigation and then detection of weeds and diseases in the field, in the crop field using image processing and machine learning algorithms. And then identification and recommendation of suitable crops based upon the soil nature, fertility levels and climatic conditions, water availability and geolocation of the crop. So next, there will be a voice-based responsive system like alerting system for farmers, so in needed conditions. So the whole idea came from the tagline, inefficient farming activities and wastage of resources. Inefficient in the sense not producing that much of yield as expected. So these are the main things we focused on, and inefficient crop planning without proper soil analysis. So actually what will happen in India is farmers just copy the besides farmers crop. They just don't go for soil analysis or soil testing. So then harmful effects of over fertilization for the soil. So if the farmer uses more fertilization as needed, it will definitely affect the soil. So then harmful effects of under fertilization on yield. So it will definitely under fertilization, not providing required amount of fertilization for the crop. And then lack of effective irrigation and wastage of resource. Wastage of resource in the sense water. Then reduce in yield rate due to delay of weed detection. As the farmer may not be available all the time, so there will be a delay in weed detection in the crop field. So and then delay in identification of pest or disease. So the farmer may not be aware of the type of disease that the crop affected. So these are the main things we are focused on. So application scope. So our product can be used in agriculture, farmers, and then agriculture research centers, and then water scarcity zones, and coming to then development of an agriculture practice with less fertilizers. So these are the scopes of our project where it can be used. So methodology. The above proposed idea is designed initially as a real-time prototype device for paddy crop. So it is tested for paddy crop, where FPGA board is used. So this FPGA board is integrated with some sensors, NPK, pH, and EC, water level, soil moisture. These are the required sensors for all the themes mentioned above. So we are having mainly 7 tasks. So first task is sensor data collection, and then crop recommendation. So after that, weed detection, and then disease prediction, smart irrigation, fertilizer recommendation. So first coming to crop recommendation. So for crop recommendation, to measure macronutrients, we need NPK, pH, temperature, humidity, and EC sensors. So these values are collected from the Kaggle, like publicly available data set. So we trained this model using a regression algorithm model, XGBoost algorithm. So and then for fertilizer recommendation, we just go for NPK and pH sensor, and we just trained our own model to recommend fertilizers recommended for the crop. So next, for disease protection, we just went for CNN model and trained. So for disease protection is done when farmer uploads the affected part of a plant, like leaf. We collected disease images of several crops like rice, tomato, potato, etc. So and then each crop contains more than 1 kmas with different diseases. So we trained a convolutional neural network model to predict the given affected plant image. Achieved 85% of accuracy on all disease prediction models. So weed detection is done. So for weed detection, we have collected our own custom paddy weed detection dataset from our village. The dataset contains 300 plus crop images with weed plants. We manually label the dataset and trained a state-of-the-art object called YOLO V5 algorithm to detect the weeds in crop. So developed a server in Python Flask to host the model and deployed it using Docker and Azure App Service. So then smart irrigation. So smart irrigation is our main goal in this project. So an automatic irrigation system is proposed based on the water level and soil moisture. Our model performs irrigation based on water requirements for crop field and stage-wise. Soil moisture acts as an essential role in recommending. So water level sensor is used as key sensor in smart irrigation too. Actually, we went for level concept in designing this project. So we modeled a condition-based algorithm to turn the motor on and off. So our model will be trained in the way that it just don't work for only water content. It just go for another features like type of soil, the phases of the crop, like that. So based on this sensor data from moisture and water level, we supply water to the crop in the stage wise. So and then coming to fertilizer recommendation. So fertilizer recommendation is done based on these NPK values, NPK and pH values. So this is our block diagram. So initially from the crop, we collect these sensor values. So these sensor values are pushed into the logic unit. Logic unit in the sense of FPGA board, Arduino, and then we push the data into the cloud. So from cloud, the results are shown in the web or mobile application. Initially, we designed a website for that one, and we are now moving to the app for better performance and farmer friendly. So the end user is farmer. So this is our model. So this model is tested in a real-time field of 5.8 meters square in our campus. So this is our model connected with solar also. So their hardware part, and these are our teammates installing the prototype model in the field. So this is the website we designed for. So a maize crop has been recommended for soil after soil analysis. So this is the home page, and we can go for the disease prediction also in the home page. So next, this is for smart irrigation, demonstration of smart irrigation. The proposed model is collected and recorded data of 15 days based on planting data. So our model achieved and saved 230 liters of water from normal flood irrigation techniques. So this is a great achievement. I can say this is a great achievement of our project. So this is all about disease prediction. So this is predicted by our model from paddy crop. So these are the images of disease part of a plant uploaded to our website. So whenever the farmer observes any unusual thing in field, he just uploads the image of the disease and just check what is the type of disease and what are the controls he should use. So we are providing 3 types of controls, like chemical control, biological control, traditional controls, all these things. So conclusion. So we have successfully done soil analysis at the initial stage, and then field is being monitored by farmer at regular intervals only. So because our system acts as a farm assistance to our farmers. So initially I have said voice-based recognition systems will give alerts to the farmer. So he need not to go to the field every time, every day. So weed is identified without a farmer in the field. So a successful disease detection model is being built where a farmer uploads a pic. The main task in agriculture, I have already told. Irrigation now becomes an automatic and successful crop gets sufficient water through automatic irrigation at intervals of time. So now farmer can be able to cultivate his crop with greater yield.
Thank you, Dhanush. Very nice work. So, any question from the audience?
Yeah, here, like in the title you mentioned it's a FPGA based, right?
Yes, sir.
So, which board which FPGA device you used for this one, and you did not?
So actually we went for D10 Nano, designed by Intel Terasic. And then we came to know that, and then we are going to implement this in real-time product. So for the cost, in the sense of cost, we are going for our own microcontroller board. So we are changing our controller board from D10 FPGA board to our own microcontroller board.
Okay. So what are the advantages of that one? So microcontroller.
So first thing is other models in our own microcontroller board. So whereas coming to this FPGA, so we are doing all the we are running all the ML models in cloud.
Okay, and one application you showed, right? So is that a mobile-based application, or what is the?
It's a website, sir.
Okay, so it is just a website. Okay.
It's a website, but as I have already told you, we are moving for Android application.
Okay.
Yeah. We are in the process.
Yeah.
So our next presentation is for paper ID 144, SV-based fast and accurate verification methodology for CTLE adaptation algorithm. And presenter is Mr. Abhishek Jadhav. Yeah. So Abhishek holds MTech in microelectronics from Manipal Institute of Technology. He has 1.5 years of experience as embedded design engineer at Select Controls Private Limited, and he has 5 years of experience as RTL designer in mixed signal IPs at Intel Technologies, and he has worked on various mixed signal IPs such as MIPI, PCI gens, thermal sensors. So I welcome you, Abhishek, for your presentation.
Thank you for the introduction. So hello everyone. So for topic for our today's presentation is SV-based system Verilog based fast and accurate verification methodology for CTLE adaptation algorithm. So in this paper or in this presentation, we're going to talk about the overview, in which we'll be talking about the CTLE overview. Following that, we'll be having a problem statement. Following that, we'll be having a proposed methodology that we'll be using to solve our problem statement. And ultimately, we'll be having one case study on which we'll be going to implement our proposed methodology, so that we'll be having some simulation result that we'll be discussing, and followed by the conclusions. So in overview, as we know, as we are going for higher and higher data rate, our channels tends to become more lossy. So just to compensate those channels, we know that we end up having equalizers, right? But as the modern day demands that every channel, these days, it's supposed to be plug and play channel. So our equalizer is supposed to be ready to adapt to each and every coefficients which will be end up having each channel. So for such adaptations, we have basically two algorithms. One is a monitor slicer based science and LMS algorithm, and another one is a phase based science and LMS algorithm. So basically, this adaptation algorithm comprises of a digital logic, analog logic, and followed by the microcontroller firmware. So these three components which we need. And so our problem statement here we define here is pre-silicon verification of such adaptation algorithm is not possible in our digital environment. The reason for that is whatever behavioral model which we use there, they are not compatible to manage frequency domain data. So because of that, we cannot actually get any convergence check for such adaptation algorithm in our pre-silicon verification. And this adaptation algorithm can be verified in the mixed signal verification as well. In MSA simulation, it can be verified easily, but again, MSA simulation usually takes times around 1.5 days or 2 days like that. But the prerequisite for that is analog circuitry should be ready. But as we all know, as an RTL designer, I know that our digital design is supposed to get closed early compared to the analog. So we cannot simply depend on MSV for our adaptation algorithm conversions. In statement 3, we have a MATLAB simulation which can easily verify our adaptation algorithm. But again, whatever we implement in our RTL or our SOC design, it can differ from our actual whatever we have in MATLAB. So we cannot simply depend on MATLAB simulations either. So these are the problem statement which we have. So basically this presentation covers frequency domain modeling methodology in system Verilog. So basically we will be having frequency domain model for analog circuitry, and we'll be using those circuitry analog models on our proposed methodology on a simple case study where we'll be using CTLE adaptation algorithm as our case study. And this paper does not cover any comparison of adaptation algorithm, or it doesn't compare even the different equalizers as well. So this is just a verification methodology that we are talking about here. So in proposed methodology, we'll be having two separate frequency domain models for CTLE as well as the channel. So here just CTLE that we are considering a simple linear CTLE having 2 poles and 1 0. And the channel here we are considering as 11.6 dB lossy channel at the 10 Gbps of a data rate mentioned in DFI 3.0 spec. And this frequency domain model which we create, we're going to test it on our science and LMS algorithm, adaptation algorithm. And so here we have some analog component basics. So first of all, there is a CTLE that we can see here, which has a single 0 and 2 poles having some gain, DC gain. But here, the second pole we are calling as a load pole that we are considering as a fixed pole, and other pole which is omega P1 and omega Z, which is a 0, that will be tuned based on our boost parameter or the control from the digital design. So basically, from digital design, we'll be getting a code which will be tuning this location of omega Z and omega P1 to compensate the actual dominant pole of a channel. So we are considering two simple channel which will be having 2 poles. One will be dominant and one will be extra pole that we are considering. So as we all know, at the end of our adaptation, we expect that 0 of a CTLE which we have, it will get cancelled out with the dominant pole of a channel. And ultimately, we'll end up having 3 poles. And same thing which you can see in our body plot here as well. The blue one represents the second order channel. The red one represents our CTLE magnitude plot, and the yellow one which is our resultant. So here you can see that at 5 gigahertz point, the loss at the blue one was more compared to yellow one. So AC performance has improved, but at the cost of a DC gain. DC gain will be suppressed because of our CTLE. And the other components that we supposed to discuss in adaptation algorithm is our bang-bang phase detector. So basically, bang-bang phase detector meant to define phase relation between our each phases, whatever we have, clock 0, 90, 180. And it will end up giving us information about our age or age sampler or the data sampler, whether it is early to our actual age or not. So here we are considering 3 clocks as an input to our sample, clock 0, clock 90, clock 180. It will be fed to the sampler, and we'll be having a data in terms of like we'll be having 2 data samplers and 1 age sampler. As we XOR them, we'll be getting late or early response. So in this diagram, as you can see here, if DN and EN mismatches, then we can call it that this is late. Why we can call it as a late? Because EN, E of N, whatever age we have, it is late with respect to our actual age. So in the below one, you can see E of N is actually early to the actual age, whatever the crossover we have. I'm considering that as the actual age there. So at the end, so basically the 2 objectives of this bang-bang phase detector is to have it in a CDR, where we will be using this particular bang-bang phase detector to align the clock phases of a data sampler at the center of a data, and age will be aligned at the edge. So same phase detector can be used for detection of over-equalized and under-equalized pulse. But the only prerequisite we have here is CDR loops must be locked so that whatever sample or clock phases we have, it should be aligned at the center of a data so that it will get correctly sampled. And the lone 1-bit pattern will be sending through on the pads. So as lone 1-bit pattern we send, because there will be less of a ISI involved in that. So we can clearly determine whether our pulse is under-equalized or the over-equalized. Here you can see in the under-equalized one, E of n minus 1 is actually coming earlier than the crossover which is happening, so the actual age. So we can call it as early. Similarly, whenever on the right-hand side you can see E of n is actually coming late to actual crossover. So whenever we get early followed by late phase response, we can call that pulse as a under-equalized. Similarly, in over-equalized case, whenever we get late followed by early, we can call that pulse as a over-equalized pulse. So here we are simply monitoring phases to determine whether our lone 1-bit pulse, whether it is under-equalized or over-equalized. So frequency domain modeling here, whatever transfer function we have for the CTLE, right? Single port, single 0 and 2 poles, that we can simply convert into Z domain using bilinear transform, where we'll be simply replacing S parameter by 2 by t into Z minus 1 divided by Z plus 1. As we end up having equation in a Z domain along with the Z domain poles, right? We can easily get equation in terms of a Z inverse and ultimately have a difference equation. So this difference equation we can easily implement in our system Verilog code. The only difference here is, so this is a digital filter, but it will be a real valued digital filter, which will mimic our CTLE. So here is the same thing. Whatever difference equation we have, there is a code snippet where we'll be using it as our real valued digital filter. Same thing we do for our channel as well. Whatever equation we have, ultimately we end up having difference equation, and ultimately we are modeling it as a real valued digital filter. So it will mimic the channel here. So the sampling frequency, how we should choose the sampling frequency. So for that, we have came up with some table here. So we actually ran, as we all know that if you use higher sampling frequency, higher will be the accuracy, but at the cost of a simulation time. So we cannot simply go for higher sampling frequency there. So what we thought is, we can get the accuracy data from our MATLAB simulations, where we actually calculated the accuracy, and we got this accuracy, you can see in the mid-central column, followed by the simulation time. We actually ran our digital simulator there for each sampling frequency, and we found out that 200 gigahertz sampling frequency is the optimum one which we can use. So again, it depends on the user's requirement. If someone wants less of accuracy, they can go for 50 gigahertz as well, no issue in that. So this is the microarchitecture that we are considering as a case study here. So basically here you can see we have two loops. One is for the CDR and one is for the CTLE adaptation. As we know that as CDR gets locked, it will be controlling our phase interpolator to give those four particular phases, which is clock 0, 90, 180, 270 to the samplers. So whatever data coming out from the CTLE, it will be sampled out and it will be passed on to the CPO, and this CDR loop continues. But we expect this CDR loop to be faster compared to our CTLE adaptation. The reason is, as we already told you, right? CDR must be locked before a CTLE gets adapted. So in this particular architecture, you can see as data gets transferred from the transmitter, it will be passed through our frequency domain channel. It will be passed through the CTLE, where will be based on the initial coefficient, whether that particular pulse will be either over-equalized or under-equalized based on the CTLE adaptation coefficient, initial coefficient. So whatever sampler result we have, it will be passed through ultimately it will pass to the CTLE adaptation algorithm, where it will take this data, 8-bit data as well as 8-bit H. It will extract, it will try to detect whether lone 1-bit pulse is there. If lone 1 pulse bit gets detected, it will be passed through the phase detector to get early and late response. From this early and late response, we can, and these are the simulation results. On the left-hand side, we can see the over-equalized pulse. On the right-hand side, we can see under-equalized pulse. On over-equalized sections, you can clearly see the channel output at the both ends. You can clearly see that whatever we are getting for the channel output, it is almost closed. So these are the digital simulator results. These are not any analog simulator. So we are getting I as really closed, but as it is having some initial value of initial coefficient of a CTLE is there already. So in left-hand side, the I is actually, you can see it is wide open at 118 picoseconds. So it is already over-equalized. On the right-hand side, it is already under-equalized. since it is over-equalized, we expect that boost to get reduced and settle to some value so that we'll get exact pulse. So same thing is happening here. You can see that boost is going down and converging at one value. And similarly, ultimately, we'll end up having a CTLA output of exact 100 picosecond. That's what our 10 Gbps 1 UI corresponds to, 100 picosecond. Same thing happens over there as well. We'll end up having incrementing in boost, and ultimately we will end up having 100 picosecond of a wide open eye at the end of a CTLA output. So from this, we can clearly say whatever adaptation algorithm we had based on the phase science and LMS, those are able to converge very fast. And this usually took only 15 minutes with FS of a 200 gigahertz. And the conclusions here is pretty simple. Whatever frequency domain model we have came up with, it actually helped us to verify our adaptation algorithm, which we have proposed. And same thing, same such frequency domain models can be used for other equalizers also, for other equalizer adaptations also. Yeah, these are my references, and thank you.
Thank you, Abhishek, for the presentation. Do we have some questions?
Bang phase detector point of view, you are using a predefined pattern. So suppose let us take a PCIe as example. You are doing for a multi-gens. Where you are pumping this predefined pattern and calibrate that for various channels.
Okay, you are talking about predefined pattern for this
bang
pulse.
Yeah.
Under equalized, over equalized pulse, right?
Yeah.
Yeah. So basically what we have done here is we have sent up simple PR-based data. There we are not sending simple separate lone bit pattern. We are simply sending a PR-based 9 data onto the pads. Okay. And we have made sure that on each transition of edges, our CDR will be
giving it to the DFE.
Correct.
Then DFE will take over there.
DFE.
Yeah, DFE. Okay, yeah. Post cursor. After second UI, the DFE will correct.
Correct.
Okay. So if you don't open properly, if the convergence goes in another direction, DFE will become error.
Correct. So okay. So here we are talking about the CTLE, and here we are considering that it will have some initial coefficient. Either it will be over equalized or under equalized. Okay, so there we are considering some scenario. It's not like that I will be completely closed.
Okay, you're starting with some initial conditions.
Some initial values, yes.
Thank you.
Of 11.6 dB lossy channel at 10.
Approximately 12 dB. So this CTLE is supposed to be gaining 12 dB or a little less than that when channel loss has to be recovered.
Correct. So,
but your CTLE in low pass filter, even at the peaking, at the 6 gig or whatever it is less than 0 dB.
Correct.
So that means it is still attenuating only.
Still attenuate means I didn't get your question.
No, go back to your CTLE outputs. 1:1.
Correct.
So CTLE is not gaining the attenuation that is offered by the channel through CTLE.
Yes.
CTLE is supposed to be recovering the whatever attenuation that happens in the channel.
Yes.
That's not happening here.
Yes, yes. So basically here we are suppressing the DC. As we know, it is passing through the channel.
That is okay. DC is minus 5 dB you are doing it.
Correct.
But AC, whatever is there at the peak frequency, it is still less than 0.
It is still less than 0. Yes, yes, you're right, you're right. Yeah. So this again.
That is has to be positive dB actually.
Again, it depends on the implementation that we have, right?
Whatever implementation you do it, channel loss has to be recovered through CTLE.
Correct.
In this, it is not recovering that certain.
Okay, okay, you're talking about that. Yeah, sure, got your questions. Yeah.
Do you have any variables for the cross corner?
So basically what we can do is whatever complexity we need in channel or the CTLE, like multiple poles, right? That we can actually have a simple transfer function we can get, and we can simply from MATLAB we can get the Z domain equation, and even the difference equation we can get from the MATLAB as well, and simply we can implement. So currently here we are considering only one case. So our main objective is to propose a methodology so that we can verify our convergence of our algorithm.
So, okay, you are trying to check the convergence of your algorithm instead of running in the analog loop.
Correct.
You are just modeling into the system Verilog and running the simulation so that your adaptation, simulation time will be less.
Correct. Because usually that's how the loop is, right?
Thank you.
So that's why this. Yeah.
Okay. Thank you, Abhishek.
Yeah.
So,
Thank you.
So our next presenter is for paper ID 186, titled as 16 Gbps third order CTLE design for serial links with high channel loss in 16 nanometer FinFET. Mr. Pranay Kumar Thota. Pranay? Yeah. So Pranay is currently working as a mixed signal design engineer 2 at Microchip Technology Private Limited, Bangalore. He holds a master degree in VLSI system design from NIT Warangal. His research interests include high-speed serial link, analog and mixed signal circuits. Yeah, so I welcome you, Pranay.
Yeah.
Please.
Thanks for the introduction. Good evening, everyone. Myself, Pranay Kumar Thota, and my co-authors are Shivakumar Rapina, Technical Staff Engineer at Microchip, and Professor Bhimarao Nistala from NIT Warangal. Today I will be presenting an idea on a 16 Gbps third order CTLE design for serial links with high channel loss in 16 nanometer FinFET. The agenda is, first I will start with the overview, then I will go through the problem statement and scope of our work. Yeah. Hello. Then I'll explain the working principle of conventional architecture and proposed architecture, along with the results and findings that we have obtained from our SIMS, followed by conclusion. Overview. The on-chip speeds has been improving over the past 20 years as the transistor size is shrinking. Now the limitation for the performance of a system that consists of multiple ICs is off-chip communication speed, which is nothing but chip-to-chip communication speed. So why off-chip communication speeds are low? For a high-speed serial link, chip-to-chip communication speeds are typically in the range of gigahertz. The channel that is present between the two chips is a lossy channel, which results in the inter-symbol interference. Because of inter-symbol interference, the digital data that is transmitted at the input of the channel may not be able to retrieve at the receiver side. So how to improve the bandwidth of the channel? So if you can see the frequency response on the right bottom, it is kind of low pass. If we design a circuit whose gain increases with the frequency up to at least till Nyquist frequency, then the equalized channel response will be flattened till Nyquist frequency. This concept is called equalization, and the circuit used to equalize the channel response is equalizer. Moving on to problem statement. Based on the length or attenuation experienced by the channels, they have been characterized as multi-chip module, extra short reach, very short reach, medium reach, and long reach. From top to bottom, the length of the channel increases. So as we know, when the length of the channel is increasing, it experiences more attenuation. You can see in the figure, the channel responses of 7-inch and 17-inch channels are shown. 17-inch channels experienced more attenuation compared to 7-inch. If you see the pulse responses, 17-inch channel has more attenuation and more dispersion compared to 7-inch channel pulse response. So in general, first order CTLEs are used for the equalizers. But here in our work, we have used long range channel, which has very high losses. So first order CTLE based equalization is not enough to compensate the channel loss. So our objective is to design a third order CTLE for 16 Gbps data rate serial link to achieve minimum I height of 30 millivolt and minimum I width of 0.2 UI for the channel loss of 30 gigahertz at 30 dB at 8 gigahertz Nyquist frequency. So scope of our work is, we have designed third order CTLE, and the pre-layout simulation results are compared with the conventional first order CTLE and second order CTLE that we are implemented in same technological node and for same supply. And post layout sim results are compared with the other previous works. So conventional first order CTLE. Here, the schematic for the first order CTLE is shown. It is similar to the differential amplifier with source degeneration, but the only difference is the source degeneration circuit has capacitor. So the source degeneration impedance varies with the frequency. At the low frequencies, the source degeneration impedance is nearly equal to RS. So let's say gain is A1. As the frequency increases, the source degeneration impedance increases and the gain of the circuit increases with the frequency. When the source degeneration impedance becomes 0, at that frequency we will get maximum gain of GM into RD. And when we move on to further higher frequencies, the pole due to RDCD gives the attenuation. So the circuit has 1 0 and 2 poles. 1 0 and 1 pole is contributed by the source degeneration circuit, and the other pole is due to RDCD. Next is second order CTLE. It is obtained by cascading two conventional first order CTLEs. So it has 2 zeros and 4 poles, which is double compared to conventional first order CTLE, and the maximum slope achieved by the circuit is plus 40 dB per decade, and max gain is GM0 RD multiplied by GM2 RD when the both source degeneration impedance of both the stages is 0. At that point we will achieve maximum gain. Coming to proposed third order CTLE, it has two stages. First stage is a conventional first order CTLE, and the second stage is a single stage second order CTLE. It is called as, second stage is called as second order CTLE because it has second order source degeneration circuit which gives 2 zeros. So at a particular frequency called resonant frequency, the impedances due to CS2 and LS2 cancel out, and at that point the source degeneration impedance will be 0, and the second stage attains maximum gain of GM2 RD. So the overall circuit has 3 poles and 3 zeros and 5 poles. Because the circuit has 3 zeros, the maximum slope attained by this circuit is plus 60 decibel per decade, and maximum gain is GM0 RD multiplied by GM2 RD. Here the frequency response of channel used and 3 CTLE architectures are shown. If you see the channel frequency response from 600 meg to 6 gig, the slope is minus 22 dB per decade, and from 6 gig to 8 gig, the slope is minus 56 dB per decade. If you want to equalize this channel, we need plus 22 dB per decade from 600 meg to 6 gig, and from 6 gig to 8 gig, we need plus 56 dB per decade. For the first order CTLE, maximum slope we'll get is plus 20 dB per decade. It will equalize the channel from 600 meg to 6 gig, but it cannot equalize from 6 gig or to 8 gig. With the help of second order CTLE, which has maximum slope of plus 40 dB per decade, we'll get better compensation, but still we cannot equalize minus 56 dB. With the help of third order CTLE, we can actually get plus 60 dB per decade, so we can equalize the channel at 6 gig to 8 gig as well. This is the motivation behind designing the third order CTLE for this long range channel. So here on the right hand side, we have shown the layout for our proposed CTLE. We have designed it in 16 nanometer TSMC, and area occupied by the circuit is 0.0018 mm square, and capacitors we have used are MOM caps, resistors are metal resistors, and the inductor we have used is of octagonal type, which is stacked in 4 metal layers from M8 to M11. Maximum Q factor achieved is 6.42. And coming to the results, here on the left hand side, we have shown the block diagram of the test bench we have used. Here the differential input data is provided at the channel input, and the channel output is connected to ESD and termination circuit followed by CTLE. On the right hand side, the pulse response at the channel output and at the 3 CTLE architectures output are shown. Here architecture 1 means first order CTLE, which is conventional one. Architecture 2 is second order CTLE, and architecture 3 is our proposed third order CTLE. You can see for our proposed third order CTLE, the pulse response, it has very less attenuation and less dispersion compared to the other two architectures. Magnitude response of 3 CTLE architectures are shown here. Our architecture 3 has got maximum gain of 19 dB, and maximum peaking gain is 19 dB minus 8.43, which is 27 dB, which is higher compared to the other two architectures. And on the right hand side, you can see the equalized response of 3 CTLE architectures. And architecture 3, which is our proposed architecture, attained very less attenuation at Nyquist frequency compared to the other two. Here the eye diagram at the channel input and channel output are shown. Here you can see the eye diagram at the channel output is completely closed. Here the pre-layout results for eye diagram for all the 3 CTLE architecture are shown. With the first order CTLE, eye is completely closed. And with the second order CTLE, it is slightly open. And with our proposed third order CTLE, it is significantly open. And in the right bottom, we have shown the post layout eye diagram results for our proposed CTLE. Here we have compared the eye diagrams for all the 3 CTLE architectures. In the first column, no equalization means without the CTLEs, we got no eye opening. So I have mentioned eye height of 0 millivolt and eye width of 0 picosecond. So with the architecture 1, still the eye is completely closed. So eye height and eye width is 0. With the architecture 2, the eye is slightly open. It has eye height of 24 millivolt and eye width of 16 picosecond. With our proposed architecture, we have obtained 123 millivolt eye height and 28.4 picosecond. And from the post layout results, we can see we have achieved 70 millivolt eye height and 35.5 picosecond eye width. Here the performance summary for our proposed architecture is compared with the other previous works. Here all the other works has used different types of channel, so it's difficult to compare, but yeah, I have given the channel losses at the Nyquist frequency for all the architectures. You can see our channel loss is very high, which is 30 dB, but still we are able to achieve better ahead compared to the works that are shown in paper 9 and 10. And compared to the paper 8, we have got 15 millivolt less, but our channel is 13 dB more. Channel has 13 dB more loss compared to this 17.2 dB. So conclusion. So we have done the analysis on first order, second order and third order CTLEs, and we have observed additional zeros in third order CTLE has provided higher frequency peaking gain compared to the other two. So the attenuation is, as the attenuation is more for the long range channels, our proposed third order CTLE is more suitable. So from the post layout sim results, we have achieved eye height of 70 millivolt and 35.5 picosecond for 30 dB channel loss with the power consumption of 6.32 milliwatt for 0.95 volt supply. So here, here are the references that were used for our work, and yeah, thanks, and I'm open for questions.
I see you are using metal resistors for your resistor implementation in the CTLE. So it will have a lot of variation, isn't it, with respect to temperature and
across PVT variations.
Yeah, when you do the extraction over various corners.
Yeah.
Yeah, it is going to vary a lot.
Okay.
How are you going to handle it?
Yes, you are right. But here, yeah, it will deteriorate based on the PVT. But here we focused on the third order CTLE design compared to other two architectures, how best we are getting. We definitely change the resistor that we have used, which will improve the PVT.
Yeah, you must be saving a lot of area.
Yeah, so 1 minute, just additional answers. I am a co-author for this. We are considering metal resistor which is of plus or minus 5% variation, and whatever 70 millivolt he has shown is with the worst case extractions. Yeah.
Yeah, another question I have is, so in the pulse response you have shown, no? The post cursor is bad. It's like it's peaking, right? It has a peaking response. Like how do you plan to compensate that?
For the architecture 2 and 3, the undershoot and overshoot are similar. It is because if you see the frequency response plot, our second order CTLE and third order CTLE has 2 poles, and finally it is attenuating with minus 40 dB per decade. And the conventional first order CTLE, it will attenuate with minus 20 dB per decade. So with the more attenuation, we got more peaking. Yeah.
No, the question is like to get the more peaking. The other end, what you are doing is you are introducing first order, ISI at the first tab. You got my point, right? So if you see the result, a green color one and blue color one, so they, what you are thinking is you are getting some advantage by getting the peaking, but the other end it is, introducing the ISI at the first tab. That has to be considered.
Yes, it will provide.
So the first tab after the, second UI, if you see, there is a more peaking towards the downside. Yes, if you come up with the best tuning, correct. Yeah, if we come up with the best tuning, we can have the minimum better dip for that. But at the same time, we are mainly considered for the main cursor, how much we are opening and giving it to a DFE. DFE will take care of the rest of the thing. DFE, if you see the curve, all the post UI cursors are very cleanly corrected. Only the first post tab or a second post tab is having a dip, which can be easily taken care by the DFE.
When you go for the pulse response or impulse response, it is rarely will go minus in the first post cursor. It will not go to minus. And as per the PCIe standard cables, it will be almost like half or 3/4 of the first cursor, which will be about 0 dB. I don't know which channel you have used which has gone to minus. That is one thing. And the other part of it is you call it as a third order CTLE, right?
Yes.
So you have used, I don't know whether you used poly resistors or metal resistors.
Metal resistors.
Metal resistors of what resistance value?
RIM M.
What resistance value?
Resistance values. So this is my circuit.
No, it's like what is RD value?
What?
RD value. That is
actually when I was working as an intern, they said to use only RIM resistors. We didn't try with the poly resistors.
The other one is you used this inductor, right?
Yes.
For the third order one, what to get.
Yes.
So inductor occupies a lot of space.
Yeah, sure.
And prone to quality factors. And your quality factor is 6. Normally above 15 is the quality factor normally people look for. So 6 quality factor may not be good enough.
Yes.
And other thing is there are a lot of applications based on the active inductor where 3 transistors can be replacing that inductor based.
Yes.
Okay. If that is the case, you will be reducing a lot of area and also the quality will be good. The inductor place can be saved. That means a lot of area can be reduced.
Yes, that's it.
Yeah, sorry, I will try to answer this. Yeah, compared to coming to the active inductors versus this actual inductors, will vary a lot with respect to channels and tuning wise. Basically variation will be more for the active based inductors. If we can characterize the actual inductors with across PVT extractions, we can really characterize in a better way and then good.
That I differ with that. Active inductors will not vary. We are using active inductors.
But
and
we need to tune it.
With PVT it will not vary because it's transistor based. Same transistor will undergo same temperature coefficients variation. So that will get compensated.
I'll differ a little bit. Okay, but our bias currents are getting generator based, resistor based or BGR based, which is coming as a tail current source. But whereas our resistor, which we are using as a load resistor, is a mass based. So perfectly the GM, the boost. No, no. Here we are using metal resistor. If you go with the active-based active-based inductor, that it becomes a load resistor for this CTLE, whose variation will not match with the resistive-based tail current source. So,
yeah. So I think there are a lot of interesting, questions and discussions happening around. Maybe we can take it off. Thank you, everyone. And I would like to thank our student volunteers for this session, Chetna and Srinit for their wonderful cooperation. Thank you.
Abhishek, I saw your name multiple times while creating the awards. So really excited to see you participate in many of the sessions and all of these things, right? Thank you for hosting this session of Sensors and Wireline Communication.
Thank you.
You have many things, so I consolidated all of them together and kept. Yeah.
Thank you. Thank you.
Yes, Mr. Arup. Yeah. Hi, Arup. Thank you for hosting this session. Thank you.